We are live. Hopefully we're live, everything is working. Welcome everybody and good afternoon. Welcome to this year's 2021 AI2S Christmas seminar, which has been co-organized by the Department of Mathematics here at the University of Trieste and the Artificial Intelligence Student Society, which is indeed also based here in Trieste. But most importantly, we want to really thank you, our guest for today, Professor Alfredo Canziani. He is a fellow Triestinian and started his academic career here at the University of Trieste with his bachelor's and master's in electric and electronic engineering, and now is working as an assistant professor of computer science at the current Institute of Mathematical Sciences at New York University. Here he is researching on topics about deep learning, indeed, but not only he is a really world-class researcher on deep learning, he's also a remarkable educator on deep learning and creator of really stunning educational contents and visualizations about deep learning. And one among many co-author of spring semester deep learning course at New York University, which is co-taught with Professor Yannick. He's here today to give us a gentle introduction and help us unravel the mysteries of energy-based self-supervised deep learning, which is kind of a hot topic today, and maybe even something more, time permitting. So really thank you again, Professor Canziani, and enjoy the seminar, everyone. The floor is yours.
Thank you very much for having me here. It's a pleasure and honor to be lecturing at home, right? It's like, you know, I'm from here. Finally, I get to actually talk about the stuff I'm doing here at home, right? So it's really, really nice. Moreover, it's also very funny the fact that this lecture was not ready this Monday, right? So I just put together the slides in a few days, 2 days. So please be, you know, nice to me. I guess you won't have a super polished lecture as you may expect. Because again, things were like put together the last minute. Moreover, I had to thank Jan because actually he really spent some time yesterday in trying to make sure I'm not going to say, you know, crazy things. So he checked everything. Everything should be rather accurate. Although he hasn't seen the last version, so might be something went through. And so, what is the plan for today? So today I will start with this topic over here on my back. Where I will tell you a little bit like a survey about the, the literature for the latest news on energy-based self-supervised deep learning, right? That's the first part. So the first part might be not that accessible because it's really the top edge, like the frontier, the latest news. Then I was thinking to have two following parts. The second one would be a gentle introduction on energy-based model where we learn how to use these models, how to play with them, so how to actually use them, so inference, and then how to train them, how to learn the parameters. And then again, if you're still awake and with me and willing to go through the third part of this talk, which you don't have because I guess, you know, I'm taking over the time that I have, I will also give you a more in-depth, explanation about one of the topics I'm covering in this first part, okay? So I will go with this kind of introduction of the literature. I will give you a lecture, which is going to be, you know, accessible for these EBMs, energy-based models. And then later, the third part, which is going to be a little bit more, with more advanced topics, okay? So I guess you can choose to leave at any time. Maybe just wait for the break before, okay? Moreover, I'm here for communicating, right? So I'm here to say something, I guess, and make sure you actually catch and perceive and understand what I'm saying, right? So my English may be not, that good. So As soon as you cannot understand what I'm saying, or I'm saying weird words, you have no idea what's going on, stop me. Say, I've stopped. I have no idea what you're talking about. Repeat or explain again. Just stop me, right? Don't get lost and don't doze off, right? Because if you turn off, I can't turn you on, right? I can't go there next to you and shake you up. We are not undergraduates, right? If you are in undergraduates, I might come down, but we are, stay awake. I can't keep you awake, but we try. But stop me if you are lost at any time, okay? So we have this agreement. You stay awake, I try my best to communicate. Huh? Yes? Okay, you understand. Very good. Also, we are streaming live worldwide. So we are on YouTube. If you have any question and you're not in class, just feel free to type them in the YouTube chat. I have here all your comments, so I will try to address any of your questions live as they come. So let's get started. Let me switch the camera for the people at home such that they can see the slide. There we go. So now you can see the slide, and I'm on the box as usual. And we go start. Okay, so today we talk about this energy-based, self-supervised deep learning. So many words. I think deep learning, you must know what it is. If you don't, you're in the wrong place, I think. Energy-based, you learn today about a bit more. In the second part, I will tell you about everything about that. Self-supervised is actually the main topic of the first part of the lesson. What are we trying to do? So we are trying to capture dependencies between our variables, predicting everything from everything. That's self-supervised learning, while handling multimodality and stochasticity. And that's the energy-based approach, right? So we use this energy-based model to handle multimodality and stochasticity. We predict everything from everything. That's the self-supervised learning. So again, self-supervised learning, predicting everything from everything, right? We start with this pink box, which if you have seen my videos online, you already know this is going to be my X. This is my observation. This is what I have. And on the right-hand side, I have my blue box, my Y, the blue bold Y. So the pink bold X is going to be my observation, what I have. And then the blue bold Y is going to be what I try to learn. Okay? In this case, I represent, let's say perhaps we have time on the horizontal axis. And so I may want to predict the future given the past, right? Like, let's say we have like a language model. I'd like to predict what is the next word when I type some other words in your mobile phone, right? Or, for example, I have a sentence in English, and I would like to produce and predict what is the equivalent in Italian. So we have translation, right? So this is basically a classical type of conditional prediction, right? So we predict the blue stuff, the target, given that we observe something else, like the Italian version of the English sentence. We have seen the speech, and we do speech to text, right? So this is going to be audio, and we produce as output like some textual description of what we heard. Right, so this is like given one, produce the other. Or we can have a more interesting version where we have a few samples. So the pink are the one given to us, and then we try to fill in the blanks, which are the blue parts. The blue are the missing one. During training, you have both of them. And during inference, we're going to be trying to fill the gaps, the blue parts, given the pink one. This is an example of masked language modeling. You have a sentence, you delete a few words, and then you try to predict what are the missing words, right? If you train a model with this strategy, you get a model that is able to fill in the blanks, which is, knowing what to put in that missing part. Okay? The same I'm doing with you, right? So sometimes I make some sentences, and I wait until you finish my sentence. See? Perfect, right? So I'm playing with your language modeling, right? This was like the first type, right? I gave you the past, you predict the future. But I can say something for it. I can just skip words, so you can fill in the missing parts, right? So that's the other version. That's actually what happens when I speak. And if you know the language I'm speaking, you can actually understand what I'm saying, right? Mom in the back might not understand what I'm saying because might not understand English. So although she perceives all the audio I pronounce, I create, but without having the language modeling model, you cannot for certain, pick up all the sounds you produce, okay? So this was like that, and then we may have, even more. I can produce some depth, some upper part, lower part. You may have like video prediction, where you produce half of the screen given the other half, or the upper part given the lower part, or some part in the future given some part of the past, right? So you can do any kind of combination, right? Why on earth do we care to do something like that, right? Why is this useful? Two major reasons, right? So the first one is that we can learn hierarchical representation of the word. And with that, basically, that basically means that we can use this learned representation of the word for performing later on other downstream tasks, right? So let's say you want to do image classification or something like that, right? So how do you train your model? You give many images, many targets, right? The labels, and then you try to get the model to connect your images to your targets. But then how much data you need? How many images? How many labels? Little or many? Do we know? What is the major curse of deep learning? Tell me. Okay, I'm making the question again. So let's talk about supervised learning, image classification. I'd like to train a network to learn the label of a given image. Okay, how many images and how many targets, labels, do you need in order to train, let's say, a ResNet, whatever architecture? You need just 10 points, 10 images. You need 100 images. You need 1,000, 10,000, 100,000, 1 million. Tell me, how many data points do I need in order to train a deep model? Few? Many. Many. Okay, very good. Until here we agree. Second part, who gives you the target? Who gives you the labels? When you do image classification, who gives you the labels?
You want curator or somebody.
A curator, right? Someone you have to pay, right? You need a person, a oracle, right? And this oracle costs, right? It's a human, right? You have to pay him, her to provide you this service, right? Guess what? This is the major bottleneck of the field in 2021, right? Every possible company that is using deep learning is facing the same issue. They had to spend a lot of money to collect a lot of data which needs to be labeled. And the labeling cost is the major component that costs you money, right? So guess what? Everyone is interested in this. Why? Why is that? Because you can just spare money, right? That's the whole point, right? We all here because we'd like to, spare money, I guess. Or make money, right? Either way. You can make money if you spend less, right? All right, so why do we care about this? Because we can learn a representation of the word. And then what? And then we just need a few samples in order to train your network, your supervised network, right? So how does stochastic gradient descent, let's make a parenthesis, right? How does stochastic gradient descent? You have works, you have your model. Then whenever you have your model, you initialize it, right? So you have in the parameter space, you start with a point over here. Then what do we do? How do we train a model? This is my random initial parameter, uninformative, sample from a prior. What happens when I train a model? Tell me. Yeah, this is a lecture, right? You have to talk back because otherwise you don't go anywhere.
You move it.
I have to move it, right? In the parameter space. How do you move it?
Try to move it down following the gradient.
I follow the gradient. Which gradient?
The one you calculate using a batch.
So
Part of the network.
correct. So the batch, the gradient I follow, it's a stochastic approximation of the gradient that tells me in what direction to go. Why is approximate version? Why is stochastic? Because I only provide the network one batch, right? I don't provide the whole data set and I have one direction. I just provide a few samples and I have, you might go that direction. Okay, I step there. Actually, I went up. Damn. Okay, I try again. Another batch. I step that direction. Okay, that one actually went down. Then I provide another batch and I get a new gradient. I step back, right? So how far can I go from my initial location? So we go we just go somehow downhill, right? Sometimes we go up, but then mostly downhill. But then how far can I go from my initial location? What is my propeller? Not propeller, what's it called? What is my gas? What is my
Data.
the data? Which type of data? the labels, right? The more labels you have, and the more you can go far away from your initial uninformative location, right? Okay, very good. Where do we stop? When does stochastic gradient descent stops?
When we tell it.
Say again?
When we tell him to.
When we tell, sure, okay. But when does he slow down? Let's call it like that, right?
Minima? Local minima? Or
Local minima. What happens in a minima of a function, of a scalar field? Gradients are 0, right? So if we move proportionally to the gradient is 0, you don't move. Very good. But if you have the actual gradient, you don't have the actual gradient. You have this kind of stochastic gradient, no? You have somehow on expectation it is 0, but sometimes you get some gradients that moves you around, right? So what happens if you have a narrow minima? You hit an edge, you're gonna get a slope, poof, jump out, right? Until you end up in if this was narrow, this is a wide minima. Very good. So when you end up in this wider minima, you go around. Also, if it's stochastic, doesn't matter. You stay captured, right? You get caught in this wider minima. So we start from this uninformative initial point sample from the prior distribution. We go down somehow on expectation, and through the stochastic version of the gradient until you end up in a, finish the sentence. Which kind of minima? A wide minima. Very good. All right. And how far did we go? As far as we have which type of data? Be specific. Labels. Very good. And the labels are what is expensive. All right. Guess what? Here there is a much wider and lower minima. But we can't get there because we don't have enough money. Very good. Awesome. Okay. So how on earth can we get on the larger, flatter, and lower minima? Lower means better performance, right? Well, you have that stochastic gradient descent solution depends on, what was this thing? The initialization, right? So as you move this thing over here, you end up further away, right? Awesome. So how do we move from here to here? Over here, okay? So learning a hierarchical representation of the word allows me to come up with an initial value for my stochastic gradient descent, which is no longer this uninformative prior that comes from whatever Gaussian distribution, but we start from an initial point which is understanding the word already, right? And then from there we can do stochastic gradient descent until we get into poof, wide minima. I hope you like the sound effect. All right. First part. Second part, we may use this stuff here, this is self-supervised learning, the predict everything from everything, for learning a predictive forward model of the world. Okay? Why do we care about this? So we learned the first one, right? Which is this is really important. Okay? So everyone in the whatever called in the industry, it's super interested in this, right? This is where dollars come out, right? Well, yeah, this is one for the economical interest. This stuff here, why can we care about learning a predictive model of the world? How do we send a shuttle to the moon? Do we know? No? So we use optimal control. We have a model of the world, usually. We know what is the physics, right? You know what is going to be the next state given the previous state. So we have some differential equations. And then we minimize the overall distance to my final target with respect to my control input. So I have let's say, my rocket. I have to provide some input such that my differential equation lands to the moon, right? And I can shape this equation, right? I can shape the curve by, for example, minimizing the distance to the final target, okay? And so this is what we may use this predictive model, right? This basically language model if you want it, right? I'll show you another slide later on about that. And that's it. Questions? Are you with me so far? You understand my English? Are you having fun?
Yes.
Okay, very good. Me too. From home, no one texts. Are you online? Are you actually hearing? Are you enjoying the thing? Say something if you're online from online. All right, next. How can we go ahead and try to do what I was telling you, right? How can we predict the blue ball Y given my pink ball X, okay? So let me start with a simple architecture, right? So I'm gonna be connecting my pink ball X inside a predictor, which is predicting the hidden representation of my blue ball Y, my target. And then my hidden representation, the green ball H, is going to be fed inside a decoder. And so we go from this internal hidden green representation through the decoder to give me some circa Y, right? This violet, ball Y, violet tilde, Y tilde, right? The tilde means more or less, right? So how do we train this stuff, right? So we feed my input through a few layers of a neural network. I'm going to get a output. Here I have my target. What shall I do right now? How do we want to have this output with respect to the target?
Identical.
We want to have an error term here. We'd like to minimize this error, right? So the training of this system will be performed by this minimization of this error cost, this cost term, which is measuring basically the distance between my blue ball Y and the violet ball Y tilde, okay? All right, so I just do this, okay? I train this system, and I have this particular type of data. Let me tell you a little bit what this stuff is. So this is a top-down view of my neighborhood of my vehicle, my car, okay? The blue vehicle, the blue item is my own car. The red lines are representing the lanes on the street. And the green rectangles are representing other vehicles near me, okay? And here I will show you 150 frames, which is 15 seconds of future, of evolution of the history, of the whatever I recorded here. This instead is gonna be, so this is gonna be my blue ball Y, okay? Blue ball Y is a sequence over time of frames, which each RGB color represent the length, G is going to be the other vehicles, B is going to be myself, doesn't move, okay? This is going to be my Y tilde, the violet bold Y tilde. That's my output of my model, okay? So let's look at the next 150 frames or 15 seconds. So as you can tell, roughly 5 seconds in the future, the model output is just crap. And when we reach 15 seconds, you have a very blurry version of what the model expects to be the future. What on earth happened here? Okay, let me play again this animation, right? Oops, sorry. So again, this is the actual future, and that's my deterministic prediction, which is the output, my Y tilde. And you can see that usually, as soon as we hit the 5 seconds in the future, things get really blurry and really not as crisp as the actual reality, right? What happened? Can you tell me? Do you know? You already watched my lessons. For the one that haven't watched my lessons, do you know what happened here? So let me try to give you an intuition for what happened here. So let's say I have a pencil. Okay, I have a pencil vertically pointing on a piece of paper. Okay, since I cannot draw 3D because I just use PowerPoint, let me draw a top-down view. Okay, so I make the pencil fall a few times. Okay, so it will fall in these locations. But my model, so those red points are representing my blue ball Ys, right? The targets. Those are what actually happens in reality. Given the initial condition was me starting in the center, right? What's going to be the output? What is going to be my Y tilde, given that I minimize the distance between my output and all possible outcomes? What is the average outcome there?
Roughly the center.
Yeah, okay, my mouse. So, yes, so there you go, there was an animation going on. Exactly, so what does my model tell you?
It falls in the center.
Exactly, it doesn't fail. Doesn't fail, right? And is he right? No, it's wrong. So how can we fix this, right? So the issue here, the one I showed you before with the cars, is that everything may happen, and so the model produces an output which is showing me everything. Meaning a car will go to the left, a car will go to the right, a car goes forward, a car goes backward. What is the outcome? This car basically expands and it becomes blurry, right? It becomes blurry because it's going to be lowering the intensity. It's like a probability, right? Before it was a binary, right? What's called the opposite of stochastic? Deterministic. Yeah, it was deterministic, like 1, 0, right? I had a car in this location. A few steps in the future, well, I'm not entirely sure. So I put a bit of probability mass here, a bit of a probability mass there. So this stuff gets fainted and enlarged. Oh, okay. I see comments from online. Yes, that's a regression to the mean, Ricardo. Correct. Right. So let me show you again this diagram, and let me show you, visualize what's going on here, right? So we have that this y can take many possible values. They're represented as all the points in an ellipse, right? There are infinite points in an ellipse. But then I start from one point in history, right? Given a observation, given that I have a starting point, my initial location, my predictor will produce one hidden representation, and therefore the decoder will produce one expected outcome. And I try to get the one expected outcome to be as close as possible to every location in an ellipse. What is going to be the solution? To get this point as close as possible to any of these points. Well, it's going to stay in the center, which is known of the points that actually happen, right? So the blurry image you saw before, which is the average solution, well, it's not a valid solution. That will never happen, right? So future is multimodal. Future is stochastic. From an initial condition, I may go in every possible direction. If I just produce one output, well, I will produce the average future prediction, which is going to be a blurry prediction. All right, so we have identified an issue, which is, we can't make this stuff work as it is right now with a feedforward network. Therefore, we're going to be introducing these energy-based models, capture dependencies through an energy function, right? So we no longer have this kind of function that is mapping my axis to my y tildes, where these y tildes are approximations of my y's, but I have to come up with an alternative way of encoding compatibilities between inputs, x's and y's, okay? Are we all together with me? Are you all good? No sleeping people. Very good. Okay, success until for the first part. And we are 40 minutes through. Okay, so this was my first initial model I showed you before, right? This stuff is amazing. Okay, sorry. There we go. All right, and so here we have this feedforward model where my output, the violet, bold, y tilde, is produced in a finite number of steps, right? So I input my x in the predictor, I compute an h and goes through the decoder. After a finite steps of computations, I get my y tilde. On the other side, on the right-hand side, I'm going to have some relaxation of this type of architecture. So I have this pink ball x, I have my blue ball y, and these two are fed inside a big box, a F big box, right? And so this is my energy model, where inference is performed through energy minimization. So given a observation, given an x, a pink ball x, how do I find what is the corresponding blue ball y's plural, right? Well, like that, right? So this y check, which is the output of a minimization, that's why there is the check points downwards, right? Is the minimization of the function f given x function of y. Okay, so that curly y means it's a function of the y. And so I try all possible y's in this big curly y, and I return which one is the minimizer one, right? And this one doesn't say that the minimizer is a point. The minimizer can be the whole ellipse I was showing you in the diagram before, okay? So y can be a whole manifold which has, equal low energy value. So right-hand side, energy-based model, left-hand side, feedforward model. But is a feedforward model an energy model, a restricted energy model? Yeah, of course, right? So I can, okay. Before that, x is optional. We don't necessarily need to observe my x. I can only potentially have an f of my variable y. And that's going to be the unconditional case. We just learn let's say we just learn Italian without going from English to Italian. Or we just learn a speech model without going from text to speech, right? We just learn one mode only. I was saying, is the left an energy-based model? Well, yes, why not? I can just put a dash box here, which I call f. And so you can see these x, pink ball x and blue ball y are entering this dash box with the f. And this f is called my free energy, but let's call it just energy for the moment. Okay? All right, so depending on the type of y, if y is continuous, I can use gradient descent, like conjugate gradient or something like that. If y is discrete, I may use like exhaustive search, I may use dynamic programming, or simulated annealing, or gradient-free optimization, okay? I guess too much detail. All right, next. In this case here, my free energy, my energy of the pink ball x and the blue ball y is going to be simply my cost, which is again this distance between my target and my prediction, okay? So it's just an equivalence, but then here we change the variable names, right? So you have this violet ball y tilde is function of the x, right? And so here I just change the name of the function. All right, let's see what's next. Okay, questions about this stuff so far? No? All right. All right, so there are two major types of energy-based architecture. We have the first one, which is the latent variable generative energy-based model, which is, I will shorten it with LVGEBMs. And then we have these join embedding methods, which are super popular these days. And that's going to be my gems, okay? So let's figure what these two type of architectures are. On the left-hand side, we see this latent variable generative energy-based model. I have my pink ball x, which is my point, my observation. This stuff goes through a few layers, which I just here call them encoder and predictor. You can just think about as being one thing overall. Then here I will have a hidden representation, which is again a point. And then this goes inside the decoder. But now we are going to be introducing something more. We saw that this one was not working, right? Because we have a point. We were also getting a point, and we were trying to compare a point to a infinite many points, right? A manifold. So here we introduce a latent variable, which is going to be for example, in this case, variable that moves along a line, okay? And so the decoder now, okay, I also need to feed this latent variable inside a regularizer. What is this stuff? Why do I need that? So if I don't have this term, this latent variable is too free. It can take too many possible values. Instead, this regularizer will get angry as soon as I start taking values that are perhaps far away from 0. So this allows me to limit how many values this latent can take. So it's going to be like a restriction over my power over the latent. I'll tell you later about why this is very important. So now I can produce a prediction, a y tilde, that moves all around, for example, a circle. for example, if I go from 0 to 2 pi here, I may be able there to expand it in two directions, right? X and Y in the two coordinates. One is going to be the cosine of scaled by like a times cosine of the z. The other one is going to be b times the sine of the z, right? And so now we can move in the two-dimensional space around the manifold. Given that we have access to this latent, it allows me to move around, okay? Okay, this thing, I hate it. All right. Yeah. Oh, okay. Let me see. Requirements of f should be a given class of functions. So f should be smooth, and f is going to be, I will tell you a bit more about f in the next slide. Thank you for pointing out that. How x is optional for f? All right, so second part, yeah, from the previous slide, right? Here we mentioned that x might be optional, right? So if we are doing standard unsupervised learning, then we only have targets. We're going to be trying to learn something about my data. And I don't necessarily have anything about x's, okay? So when we have x and y, we want, like, for example, as I said before, going from some speech into a text transcription. But perhaps we don't care to go from speech to text version, but we may just want to learn a language model. And so I just learn the target, regardless, without going from another space. So this is why x may be optional. And let me see. Can you give a concrete example of an architecture encoder, predictor, decoder? Yes, those examples are coming later when I talk about more specific details. This is going to be a high-level preview. And then how EBM is different than feedforward net. While both have same cost function, loss function. So the left-hand side is not, right? So the left-hand side, this energy-based model is one type of energy-based model can be implemented through the utilization of a feedforward network. But this is going to be limiting because, again, here, my x, given one x, I will have just one output there, which is connected to, like, it's going to be, we measure the error between these two. On the right-hand side, I don't show you what's inside. I can have any type of architecture. So the right one is more generic. I don't necessarily have a feedforward model inside. More about this in the second part of the lesson. More questions? I don't know what's going on, but it's fascinating. Okay. I'm enjoying online. Very interesting. Okay. All right. Awesome. Okay. Thank you for letting me know there were questions. Also, so you in class, right? If you have troubles understanding what's going on, do ask questions, right? Otherwise, I don't know whether you're following or you're bored or whatever, right? Tell me, it's boring, we want to take a break, okay? Break in 10 minutes. Wonderful, prego, okay. All right, so back here, right? What happened here? Okay, so here we were trying to get now I can compare this ellipse to this ellipse, right? I have infinitely many outputs, and I can compare them to infinitely many targets. All right, so let's try to do this to our previous model, right? The one that was not working. So overall here, I can put everything inside this box, and I'm going to call this one also an energy, but this is going to be my capital E. And so this energy now is going to be a function of x, y, and z. And in the specific, it's going to be always the sum of all the boxes inside the module, right? So we have the C, the cost term, which is telling me how far my prediction is from my target. And I have this regularization term, which is constraining the amount of volume that this Z can take, right? I limit myself in a subspace, in a small region. Otherwise, this stuff will overfit. All right, so what next? Now, next, we're going to talk about these gems, right? So this is the first one. Latent variable, this guy over here, the orange bold Z. Generative, because I produce something. energy, because I have an energy-based model, right? Overall model. Next one, joint embedding methods, right? So we're gonna talk about this joint representation. So I start with a pink ball X, which is again a point. I send it through an encoder, a projector, same as here. Well, that was predictor, is projector, same thing. And I'm gonna get this E of X. That's my embedding. My internal hidden is the same color, right? So it's a hidden representation, basically, for my X, which is also point, right? Point, point. On the other side, I have my blue ball Y, which can take infinitely many possible values, right? It lives on a manifold. And then my first encoder basically will unwarp this manifold and make it just linear. Finally, my projector will project down that line into a single point. Now I have a point on the left, I have a point on the right. I just try to make the two close together. Okay? So on the left-hand side, we have that the stochasticity or the multimodality of my target gets matched by my multimodality of my output, which has been introduced by this free parameter. This is called free parameter, right? I have this optional value I can change. So my additional degree of freedom allows me to parameterize this output, manifold output. And then I compare the two manifolds in order to make them similar together, right? Similar to each other. So this is the generative because I produce the same. In the other case, I have that the right-hand side, the right branch, eats away this stochasticity, this multimodality. In the first part, it unwarps it, and the second part, it projects down to one point, such that I can compare to this other point, right? So here we have an invariance. This stuff works because of an invariance. This stuff here works because of introduction of a degree of freedom, this free parameter. All right, so again, another box. That's also an F. F because there is no Z. So either you have E of X, Y, Z, or you have F or X of X and Y. And so there we have my F of X and Y, which is simply this cost term measuring the distance between the two embeddings. Okay? Yep. How is Z given when training the model on the left? Yes, so training, next slide. Very good. I will answer in the next slide, okay?
I have a question.
Yes.
So the y variable, do we have like a set of samples out of this manifold, or do we have like a description of the manifold?
Oh, you always have samples, right? So you have samples, but you can have potentially infinitely many samples, right? And they are all coming from this. I think this is the data generation distribution, data generating distribution.
Targets are expensive. This means that.
Second?
But so if we said at the beginning that having some target is expensive.
Depends. So what I said before, expensive is to get labels. Why are not labels? This I'm getting back to this part over here, where we only have data. I have 10 hours of recording, video recordings. Now I partition my 10 hours of recordings into X's and Y's. Half of given the my 5 last lecture, predict my next 5 lecture. I wish this was working so I can have the lectures down for free. But the point is that X and Y's actually are the same thing. The whole thing is a piece of data, and then you decide what you want to predict from what. What you start from is going to be called pink ball X. What you're going to predict is going to be called blue ball Y. Make sense? Yep. So there is no labels here, not at all. And X and Y are the same type of data, right? This is maybe an audio, a speech. Okay, it doesn't have to, right? This could be speech, this could be text, or this can be English, that can be Italian, or everything is just a piece of video, or everything is just text, or everything is just audio, and you try to produce the future audio given the past audio. So there is like a lot of freedom, but these are definitely not human annotations. All right, good question. More questions? Yeah?
The next slide
Next, the previous one, you mean?
is the last one we've seen.
Yeah, one sec. There we go.
So the gen model, how do you make the prediction then?
Ah, you don't.
Oh, you don't.
You don't, right? But the point here, good question. So the answer is I don't necessarily know, but the point is that we'd like to train this encoder. So we are back into the finding a better initial location for my stochastic gradient descent, right? And so you basically would like to find the parameters for the encoder, your ResNet or whatever, without using labels, right? And so you train your network, so you get the initial parameters from where you can start your fine-tuning for your downstream task. So both these architecture have an encoder, and the outcome of the training this system, one of the outcome of training both of these systems, the joint outcome of training both these systems is having an encoder with pre-trained weights, which you can use later for other tasks. Okay? So you want to extract as much information from the world without using human annotation, which is expensive. And so the more you learn, the more you extract in this phase, and the less amount of supervision you will require later to find an equivalent minima, or you can find a better minima if you use the same amount of labels. Two things, right? So before, when we were moving, you can use less samples to find the same solution, right? We started here, we went down to this location. Now if I start here, I just need way less samples to get here. So either you use less samples, spare money, or you use the same amount of samples to find a better minima, better performance. So outcome of training these two systems, getting parameters for the encoder. Additional outcome of training LVGEBM, you have a predictive model which allows me to later on use it for optimal control for driving a shuttle, let's say.
Okay, and sorry, it might be a stupid.
No stupid question. There are no stupid questions.
This procedure tells me that I'm actually going closer for the gradient descent to a task that I didn't give. So
Right. That's totally correct, right? So the point is that if I ask you to drive a car, I don't have to teach you, oh, that's a traffic light, that's a pedestrian, that's a dog, that's what's called a zebra, the crossroad, right? That's an intersection. You see those things and understand the meaning of what you're seeing, like without me telling you, or maybe I just tell you once, oh, look, that's a traffic light. If it's red, you may not go, right? Otherwise, you may cause an accident, right? When you talk about networks that are initialized with your initial random position, the network don't know what red, what traffic light, what corner, what intersection, what anything is. So these networks, when you train them from scratch, have no idea about how to perceive reality. They have completely, you start from tabula rasa, right? You have absolutely no idea where you're starting from. So this procedure here basically distill knowledge from reality into this model, such that the initial location where you start actually is an advantageous position because it already knows what things look like. And then you simply say, oh, okay, this is a jacket, that's a table. But I already see, I can see. Just tell me the word and I learn the word. So that is just a little bit further away from after you actually see things, right? Is it clear?
yes, it's like you compute an initial representation of your data without knowing anything.
Correct. So whenever babies learn how to see, you don't teach them how to see by telling, this is a dog, that's a cat, that's a cat, that's a dog, that's a giraffe, that's a dog, that's an elephant, that's a dog. Wait, I understand that's a dog, fine, right? So the kids, right, learn to see without you telling them constantly what the thing is. I can see what that thing is. You just tell me it's called dog, cane, whatever, right? Same here, right? So this procedure over here allows the model to learn about reality and the structure of the hierarchical composition of the reality, what I wrote before. And then later on, the downstream task will use the capabilities of this model, the visual capabilities to perform a task, which can be computed afterwards with another module, right? I just take this away. I leave everything there. Okay? More questions? Good question. I mean, thank you, because you let me explain everyone what's actually the point of this stuff, right? For me, I mean, I've been seeing this stuff for the last 10 years. I kind of forgotten what is not, obvious. Right? Sure.
We don't have a predictor in the end with the gem model.
Right. Because predictor to me means I predict the hidden representation of my target.
Yeah,
So I move from my X space. So this is my X space. I encode my X space. I still am in X space, and then I do predictor. I jump towards the other
you're
space.
running something deterministic there.
Sure.
In the gem model.
Both of them are deterministic. So this one actually, there is some invariance.
But I mean, like the decoder is somehow transforming a latent space with a certain distribution. So I have output y tilde, which is manifold. Like from the same input, I get multiple outputs.
Right. So this one could be
in the other model, from an input, I can get only a single output, right? In that sense.
So this branch, so we have to deal with the fact that we have infinitely many values here, infinitely many values over here. In this case, we match these many infinite values through the addition of infinitely many one degree of freedom. Basically, I move on a line, therefore I can move on a circle. So here we introduce this degree of freedom. Here we eat away the degree of freedom. So either you eat away the degree of freedom or you introduce the degree of freedom. Right? So there are two options. More questions? Yeah, what's up?
Maybe I lost something
Go ahead.
in the middle of the speech, but can you just tell me what is the difference between the predictor and the projector?
I didn't tell you.
Okay,
So semantics, predictor moves from my X space to the hidden representation of my target space. Okay, so predictor, so encoder, I stay here. Either I encode X or I encode Y. Predictor allows me to go from the X space to the Y. Okay, so predictor is what bridges the two spaces. Just semantics again. Projector projects a line to a point. That's it. It just kills. So this basically unwarps, right? So whenever you have so the manifold, input manifold of the data is all cramped up. These encoders are making it nice and smooth and linear, and then this projector simply kills dimensions, basically, such that I can compare the two things. More questions? Don't be shy. Yeah, what's up?
I mean, these are energy-based models depending on the form of C, because if C is a construction loss, this looks standard to me. It's the fact that C is a generalization of the usual losses that we have.
C is going to
be an energy-based model.
Not necessarily. C for me is going to be here my quadratic MSC. Okay. Quadratic distance, square Euclidean distance between my prediction and my target. What's interesting here is the fact that I have an additional degree of freedom inside the model, and the way we compute the output in this energy-based model is through the arg minimization of the free energy. So I have an energy. The energy is the actual output of every model. Given an energy, I have the freedom now of associating one input with many outputs. If you want to do a translation between Italian and English, there is not only one translation that is correct. There are multiple ones. And so each of these multiple translations will have its equivalent low energy value, right? So all of these, so this energy formulation allows me to handle multiple predictions from a single input. If I have a feedforward network, I don't know how to do that. I have an input, I have an output. Which one? Well, I need to add an internal switch, which, if it's discrete, right, allows me to do all translation number 1, translation number 2, translation number 3, translation number 4, translation number 5. And then when you have this discrete, multiple, uncountable countable number of translations, maybe not finite, I can make the first one close to the first one, the second close to the second. So you have, let's say I have my x here. You have one translation, second translation, third translation, fourth translation, fifth translation. Then I have, let's say, a discrete latent. I come up with the first translation. What do I do? There's going to be training. Next slide. I cannot tell you things in advance, but complain if I don't answer your question in a few minutes.
You have 2 other questions in the chat.
Can you briefly explain how Predictor is implemented? No. How is that given? No, we don't give it. Why would the GEM model behave differently from the feedforward model you show early in this example? Oh, it didn't, right? So here, I have my predictor goes from 1 point, 1 point. Decoder goes from 1 point to 1 point, right? And then the gem also goes from 1 point, 1 point, 1 point, right? And this right-hand side needs to eat away this manifold thing, right? Otherwise, I cannot compare the two things. And so we never seen this inputting a manifold to this feedforward network, right? So the feedforward network needs to have these properties in order for me to be able to compare 1 point with 1 point, right? Regardless of the point I am on the ellipse, this ellipse is described by 2 parameters in location of the center. Let's say they are center in the region. I have the large, like the horizontal radius, and then I have the vertical radius, right? So all infinitely many points just compare is just represented by a 2-dimensional vector, right? I answered the question, I think. All right, next. All right, LVGEBM inference, right? So latent variable generative energy-based model. How do we produce results with this model? So I have, again, my pink ball X. I have my blue ball Y, and I have my orange ball Z. All of these 3 are fed inside this E box, right? My energy box. Cool. So I can define here my F beta, my free energy of pink ball X and blue ball Y, to be this soft mean, which is basically marginalization of my energy with respect to the latent. And so what does it mean? Well, it means that F is simply a box around that E where Z has been eaten, okay? A little bit of more context, right? So what is this soft mean? I define it here as being this log sum of the exps. So the negative 1 over beta. Beta is my coldness parameter. So how cold this soft mean is, log of the sum of the exps of the negative elements inside the energy multiplied by the inverse temperature. So beta is the coldness or inverse temperature. Again, this is, if Z is continuous, this would be an integral. And here we are marginalizing out the latent from this energy. Again, don't care too much about this, but the point is that if I turn on the AC, if it's super cold, beta goes to plus infinity, then this stuff turns out to be a minimum. All right, so you can think about F beta, X and Y to be the minimum value of the energy for the Z, or this kind of softer minimum version. But again, I usually just think about, I take the mean, okay? So this is a function of all the 3 variables. I take the value of the function where I have the minimum value, and this is going to be my free energy. More about that in the second part of the class. Finally, how do I get my Y check, my output from the model? The output of the model is going to be the argmin of this F, right? So this is going to be a function. I can perform the arg minimization, and I can find what is the Y that is minimizing this F. Again, Y doesn't have to be 1 point. It can be a whole manifold, okay? So there are infinitely many Y checks, for example. So this is how we perform inference. So let's go back finally to the example we start the lesson with, okay? This was the thing that was not working, right? Remember? We were starting with a point. We had a hidden point. We have a output point. We were comparing one point with the many possible points. This was not working because the output was the, finish my sentence, mean, right? So it was just producing a point in the center, so this doesn't work, so let me remove that thing. And how do we fix this one? How did I show you? What did I show you before? How can we fix, how can we have the output to move around in a manifold? How can we add a latent variable? Very good. So I add my latent variable, which is also going inside that R box. And now I can basically parameterize my possible output, right? My y tildes. Now they're all moving around this ellipse. So everything inside this box is going to be my capital E. And then I have my energy of x, y, and z is going to be the summation of the two terms. We already seen this before. Finally, does it work? Does it not work? So this is I'm showing you this new model, okay, with the latent variable. The first one is going to be my deterministic model, the one I showed you before. Well, the future, right, the actual future. And this is myself. I put a circle in the guy to the right-hand side of me, and I put a box in the guy behind him, okay? This is my deterministic model, the thing we saw before that was not working. Here I sampled 200 latent variable for this one. I sampled 200 latent variable from here. I sampled 200 from like a standard normal distribution for this one. I sampled other 200 points from a standard normal distribution. Pay attention to what happens to the guy in the circle and the guy in the box as the future moves forward. We are hitting the 5 seconds where the deterministic model was dying. My stochastic model with latent variable still works. And multiple predictions are performed. None of the predictions here match what happened in reality. Of course, I don't know what happened in reality, but any of the predictions made by the model are legitimate predictions, right? Things here look crisp. There are no like, infinitely long curves. They are not blurred. And the interesting thing is that in this case, the guy next to me stayed next to me. And the guy also stayed there. In this case, it went ahead. This guy didn't move. In this case, both of them move ahead. In this case, they got close and went a little bit ahead. Whereas in the real future, this one basically is in front of me to the right. And that one almost gets outside. So what we got here right now is that we end up having a model which allows me to hallucinate any possible future given the point. My initial condition, I started with a point, and there is latent variable, this one, which has been sampled from a standard Gaussian, standard normal distribution. It's absolutely non-informative latent variable. It's like random numbers, right? I input random numbers inside the model, and the model produces awesome future trajectories, right? So from one point, this was the real future, and we came out with this future, this future, this future, this future, and as many as I want, right? So you understand now the powerful, right? How much powerful these models are, right? I can generate as many futures as I want, and I can use this one for training another model later on to drive around, right? So this one gives me access to the future. Given that I steer the steering wheel to the left, what happens? Well, the world will turn to the right. If I brake, what happens? Well, the world will come to me, right? If I accelerate, the world will go, well, if I brake, the world will go slow down, right? Well, it goes in the other direction, right? So it's relative motion, but anyway. So anyway, this model allows me to have an estimate of one of the many possible futures, of many of them, right? Moreover, we can also do better. We can sample latent to generate hard futures. I can generate latents that are maximizing, let's say, the dangerousness of the future. And so I can create futures that didn't exist in reality, which allow me to, train perhaps a controller, a policy, which is going to be fed with this kind of adversarial cases, or this kind of dangerous cases. Anyway, shall we take a break? Because the next part is going to be this Kelly-Bryson algorithm, which is telling you a little bit of control. Let me see how much we have left. Okay, let me go over this Kelly-Bryson algorithm, which is telling you how we can use this model here to do something, okay? And then we take like a 10 minutes break, and then we come back, okay? So what is this Kelly-Bryson algorithm? That is performing backpropagation through time plus gradient descent. This is the thing I was telling you before, the algorithm that we use to send a shuttle to the moon, right? The fact that I compute next state, next state, next state, next state, next state, next state, given that I provide a specific control until I end up a future state. I force the future state to be as close as possible to my target, and then I optimize the control in order to get there. All right, so in case you don't remember how recurrent networks work, I have a small recap for recurrent network, okay? So we start on the right-hand side with a decoder where I have my violet, bold, white tilde. There is a cost term, which is trying to make that prediction as close as possible to my blue, bold, Y, my target. And then here I have my pink, bold, X. Pink, bold, X can be a sequence, for example, or it can be an initial condition. But let's say it's a sequence, and also Y might be a sequence. So I feed my predictor with my X. Predictor allows me to move to the other space, right? And I have my hidden representation. But since it's a recurrent network, what do I need to add? Well, I have to feed back that thing inside, right? Feedback. And so I feed this hidden representation through a unit temporal delay. So this is going to be telling me what is the value at the previous iteration. And I feed it inside the predictor. But at the beginning, I will initialize this with a 0. So usually, we had to start somewhere, right? So we have initial condition, which is going to be fed to 0. And then here we produce new future states, new internal hidden representations, H1, H2, H3, H4, given that I provide a input every time, right? And then given that I have the knowledge of what happened before. Right? Finally, I connect the hidden representation to my decoder. So what are the equations here? So my equations are the following. I initialize my hidden representation with a 0. I compute my h of t as being this module, this predictor of my previous h of t, right? T is a discrete temporal index. And then my current x, my pink ball x, at the temporal index t. And then I have my final y tilde, the violet ball y tilde at temporal index t is going to be the decoded version of my hidden representation at temporal discrete temporal index t, okay? And so again, we have this evolution of the hidden state given that I provide some sequence of x's. And given that we initialize, we have an initial condition set at 0. And then perhaps we'd like to have this y tilde as close as possible to my target sequence. Again, RNN, right? So let's figure what this, how it works, right? So RNN training, we have backpropagation through time, right? So this is feedforward, and then you produce the output. When you do backpropagation, you have to go in the other direction to find all the partial derivatives. So we perform backpropagation through time, and then we perform stochastic gradient descent with respect to the network's parameters, right? In order to match my x and my y. Control, right? This is the thing we care about today. So what's the difference? There is no more the y tilde. Here I have a x naught, which is my initial state, Earth, Trieste, no, where we start with my rocket. Then I feed this inside the predictor, which is producing my next state, which is going to be 1 meter from Trieste, 2 meters from Trieste, and so on until this rocket moves on. And then I feed the next state back to the predictor, right? And then I have this latent z. And so, given that I have an initial condition, my x naught, I have new x's, right? x1, x2, x3, x4, x5, blah, 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 until I reach the final one, which should be my moon location, my y. How do I get there? Well, we perform backpropagation through time, and then we perform a minimization of the final distance to the target with respect to these three variables. So let me repeat. We have the initial value for the state, which is going to be my x naught, 3s. Then I have my state at the discrete temporal index t is going to be my predicted version, like my prediction, given my previous state and my current control. And that's called control. You know, if you've taken the course here, it's called u. We call it z because it's a latent variable. And then finally, the procedure to perform optimal control, right? To perform inference, to find this u, right? That was training. This is inference. We perform backpropagation through time, the same as for a recurrent neural net. And then we perform gradient descent with respect to the latent, or well, the control, right? So why do we care about this stuff, right? So here you can go from initial location, Trieste, to the moon by unrolling this forward model, this predictive model, the one I showed you just before, the thing over here. I like to go from here to Sistiana by car, right? How do I do that? Well, I had to go out from here, I had to go to the car, I had to put the things on. So I have a few steps, I have to unroll this model a few times, and I have to perform the right actions at the right time, right? Until I go, I don't know, 100 steps in the future, where I reach my final location, which is Sistiana, okay? All right, so this is how we perform, how we use this predictor, my world model, to come up with a sequence of actions that let me reach my target destination, okay? All right, I think I talk a lot. For the next part, when we come back, we're going to be seeing how we train this energy-based model. Let's take 10 minutes break, okay? We come back at 3:35. Sounds good? Questions first. Hold on. Are there questions? No. After the break, right? I will read the questions online in a sec. Okay, let's take a break.
Posso anche mutare il microfono, è stato già spento spengo il microfono magari dell'aula.
Posso spegnere io?
Ah, ok, perfetto, grazie mille. Perché penso che si
Back here, yes. We are back online. People confirm online if you can hear me again. So I think it seems that people were actually following. They are just a bit quiet here, they are just a bit shy, but they actually are understanding, at least the few one I sampled, right? So maybe it was like a non-representative sample, but at least the one I talked to seemed to be understanding what's going on. Again, if there are weird parts, unclear topics, diagrams, blocks and things, do stop me, ask me what's going on, don't turn off. I can't come there and shake you off. Again, you should be keeping awake yourself. I will try my best to provide the best explanation I can, okay? And again, I prepared this in the last 2 days, so it is what it is. Switching to new layout. All right, awesome. What's up? No, okay. It's a bit, rough. Usually it's a little bit more polished. Check YouTube, right? So all my lectures are on YouTube, right? Where I add all CGI effects, where I have all things happening. My bear came to life once, and when I move my hands, things appear. Here I can't do those things, right? I have a tablet here, but I can't do that live. So watch those if you want to have more Netflix type of performance. Here, just live, me jumping around. Right, we can hear you. Ottimo Matteo, grazie. So how do we train these EBMs, right? So what we have seen so far was just inference, right? I didn't tell you how we train. I told you once we have trained a system, I can use it for performing inference with the latent to find what is the control signal that is required in order to reach destination. But that was finding the Z, the control, that's inference. What is training? What does training mean? Question to you, what does training mean? No, this stuff here, just training in deep learning. You're supposed to answer.
Set the parameters.
Find the parameters, which are minimizer of your specific task cost, right? Awesome. Before we were minimizing a cost, right? No, that's not correct, Jonathan. Anyway, I'm answering questions from online. So this one here, we were minimizing this cost for a given initial condition, for a given target, right? One data point, right? One initial condition, Trieste, one target, the moon. I unroll this basically differential equation, whatever it is, right? Discretization of a differential equation, and I have this control. When you perform back propagation in the latent space, this is, read together, inference. Yes, inference, right? So training is finding the parameters. Inference is finding the free parameters, this input, right? So I find what value of the input are required in order to map my initial condition to the final destination, okay? All right, so training, finding the parameters, right? Awesome, weights and biases. So for EBMs, there are two types of training techniques. The first one is the contrastive method, where we're going to be contrasting different samples. The second one is going to be the architectural and regularized methods together. So let's figure a little bit what this stuff means, okay? Training, first part. So we would like to find a F free energy, a function, such that my free energy of the pink ball X and blue ball Y, my observed pair, is strictly lower, is upper bounded by this free energy given the same observation, right? So this is the same condition. This is like a probability, conditional probability, right? Given X, right? So the same, given the same observation for all other possible values of Y, right? The whole set minus the one we actually observe, right? And so this is what training means, right? So you have this free energy. Let's say this free energy is going to be it's a scalar field, right? It's scalar given a vector's input. So you have like this blanket, which is going to be on the floor, and then you want to have different heights of the blanket, namely, I cannot even speak. Every value that has not been observed should have a higher height of this blanket, right? So let's see an example, still this ellipse, right? Because this is going to be the part of the second part of the lesson. So I have these observations. I have some points there. And the target, those are my targets. My outcome of training is having this energy surface, which has a value of, let's say, 1.5 or something for these regions over here and over there. And all the other values that are away from these observations have higher value, right? So this stuff is a bump in the center. Here you have this lower, basically, level, and then everything comes up, curves up this way, okay? And so training is basically, we start from a surface that is all purple, and then it becomes a little bit greenish, and it becomes yellow to the edges. Awesome. So two types of learning procedure. The first one is the contrastive type. I push down the energy at this Y and the pink ball Y and the blue ball, pink ball X and the blue ball Y, right? So I push down the energy here. And then I push up the energies at the same given observation, but points that are not the blue ball Y. And I call them red ball Y hat. Pay attention, the Y hat has a hat, and the hat is pointing upwards, right? So this is supposed to be a high energy, a contrastive sample, a high energy sample. Question for you. Let's see if you actually get it. Why is the Y hat red and why is the Y blue?
I think I missed something.
Okay, my watch tried to answer the question. No, you should answer. You should try to answer the question, right?
The color coding of the.
What is the color coding? What is the key here? I didn't show you.
Temperature.
The temperature, right? Which one is hot? Which one is cold? The red one is hot, right? So this is a high energy sample. It's red. There is also a hat pointing upwards, high energy. This is a low energy, blue, cold. Awesome, right? So this one we push down. This one push up, right? The other one, the other option is the architectural and regularized version. We simply limit the volume of low energy by construction or regularization. In this case, I actually use the construction. The region of low energy are bounded to live on a 1D manifold. This is a 1D manifold embedded in a two-dimensional space. My Y tildes can only move around one line, which is curved, but we don't care. So this one line is embedded in a two-dimensional space, but only points along that line can have a low energy. And that's how this stuff is made, okay? So that is a architectural type of, by construction, right? Because I force my outcome to live on a sub-manifold. Regularization would mean you pay a cost if you move away from your small area, right? So that's something we will see later. Questions? Okay. Training, second part. So these are a few examples. I will just go through rather quickly because it's becoming otherwise boring. It's too many details, but it's just for you having like a full review of all these techniques. So in the contrastive category, we have the push-up everywhere, maximum likelihood. Or push-up at specific locations, maximum likelihood, Markov chain Monte Carlo, contrast divergence, generative adversarial networks, Siamese networks like Pearl, Moko, Sinclair. And then finally, we push up, off manifold to on manifold. So we take things from off manifold, we force them to go back to the manifold. And then here we have the denoising or masked autoencoder like BERT. Again, the white thing are the important parts, right? So we can, the contrastive, we push down on the good guys, right? The blue one. How do you find the red one, right? So the red one can be everything else, maximum likelihood. The red one can be specific location, Markov chain Monte Carlo, or contrastive divergence, or GANs. GANs is very interesting, maybe I'll show you later. Because the GAN, you have a network which gives you contrastive samples, which need to have high energy. I think I should show you this later because it's very interesting. So let me remind me. I should talk about GANs, energy-based GANs. Okay. And also this one is very interesting because it's what the state of the art is for language modeling, pushing off manifold points back to the manifold, and we have denoising and mask autoencoders. So yeah, let's talk about GANs and those two later. On the other side, we have the architectural and regularized techniques. We either have a upper bound on the low energy volume. PCA can means Gaussian mixture models, or we may have a regularization term, sparse and contractive and variational autoencoder. I may also talk about variational autoencoder, I may take too long. We may have Lista, Suave, Biol, VCREG. I will talk about VCREG at the end of this talk. Or the third option is going to be minimize the gradient and maximize the curvature, right? Why do I want to do that? What happens if the gradient is 0? Flat. Okay. What happens if the curvature is maximum? I curve it up, right? So I want low on the blue point, and then I want it to go up, right? So these are the architectural choices or regularization choices, which are forcing to only have a finite volume of low energy areas, right? If everything is low energy, okay, what is the issue here, right? Why do we care about this? Why do we want to have my free energy for the x and y to be strictly lower than the free energy for the other points? Do you understand this point? Why do we care about that? What happens otherwise? What if I don't have this second part? Second?
Everything is low energy.
Right, so you have like a flat blanket, right? And then remember, how do we compute the y checks, the output of these models? The output of the model are the argmin, right? That's correct. Let me come up here. Where is it? Here, right? My output is the argmin of f. If f is flat, what do you get? It's everything, right? Nothing. Well, everything or nothing. So f needs to have some lower parts, right? Such that you can go down in the thing. Either a point, right? You have like a convex parabola, right? What's it called? The paraboloid? No. Yeah, paraboloid, right? You either have the paraboloid or you have like a continuous manifold, maybe, which has the same low energy, right? But still, you want to have low energy, high energy, right? If this stuff is flat, then, well, no end of game, right? All right, so let's go here back, right? So we said we would like to have this thing that has, different heights. And then we came up with these options, right? Push up everywhere, maximum likelihood, push up at location, push off manifold to in manifold, which basically tell you have a point. This is the good point. You take this point, you move it here. This is going to be the bad point. The bad point is going to be high energy. And we started from this point, right? So we took the point and we have, how far is this point from the original point? Well, the distance, I took it away, right? I'll tell you more about this soon. And here, once again, either we upper bound the low energy volume, or we use some regularization term, which are more flexible, or we do the fact we enforce that the gradient is 0, right? So we have flat area, and then we curl it up with a maximum quality. We maximize the curvature. And this is score matching, okay? Again, a lot of details. I won't be talking about most of these things, just a few of them, okay? Questions? No, okay. All right, so finally, I'm going to tell you a little bit about these two types of architecture we saw so far. The first one was the latent variable generative energy-based model, which I showed you the model before running, and that can be used for performing optimal control. And then the second part was this GEM, right? The joint embedding methods, which can also be subdivided in 4 different categories: constructive, clustering, distillation, and information maximization. I won't go into much detail here, but I'll just show you what is available, where you can read about these things, okay? Right, so here you have 4 different techniques. You can find more, this illustration has been adapted from this paper over here. So we start from the first one. It's SimSiam, one which has the left branch. You know, all of them have this encoder and projector, right? The last one has a predictor and a generator, but they are just different names, the same thing. This branch has 2 more things in a square. This branch here has 2 more. What's happening? This branch here has 2 more boxes, and then we have a final cost, right, as the things we have seen before. So we have 1, 2, 3, 4 things I should explain, I haven't explained. The second one is SimClear, has 1 box on the left, 1 box on the right, and then we have a cost term. So here I should explain what this thing is. Then we have Suave, and then we have also too many boxes. 1 box on the left column, 2 boxes on the right column, and then we have a cost term. And then the last one, Oboe, which we have a EMA, which is like an exponential moving average. So the right model is like a average of the left module. So it's like a low pass filter of the left module. And then we have a cost term, right? So everything that is not aqua, you already know, right? Yes? No? I already told you. The red boxes are the costs. The green thing is going to be the hidden representation, embeddings. These 2 are 2 models, encoder and projector. X is my observation. Y is the part that needs to be having the remotion of the, the degree of freedom, right? And then we had, this other box here. So another green thing, right? Guess what? Too many things to explain. I skip this stuff. Because next slide we have more, right? So as you can tell, this stuff is rather popular right now. And there are many people that are just adding 1 more box, and now they're actually flipping this thing, right? So far we were having all trapezoids this direction. Now we have these 2 people here flip the thing upside down, right? So, okay, yay, what does it mean? All right, let's start from the right-hand side. So we have Biol, bootstrap your own latent. We have 2 exponential moving average. We have 2 more aqua boxes, and then we have the cost. Here we have WMSC, and we have 2 boxes on the left, 2 boxes on the right, final cost. I think you understand how this stuff goes. Here we have Barlow twins, we have more boxes, so many boxes and 2 costs. And finally, we have VCRAG, which has red boxes, 1 more red box. Guess which one I'm going to be explaining to you? The one with only red boxes. Why? Because I don't even know how the other stuff works. But this one, it's the same. It's made with the same blocks I already explained to you, right? So cannot be that hard, right? Those, might require additional explanation. I don't want to be tedious, right? All right, so let's start with the left-hand side, VCRAG. So I'm going to be introducing here the following, right? So my E, green bold E, is going to be a matrix. It's going to be belonging like to B times D, right? It's a shape of B times D. Means it's a matrix of height. It's going to be the batch size, as many items you have in the batch. And then as many columns as the dimensionality of this vector, right? So you can think about having many of these ED vectors, right? So you have E1, E2, E3, E4. Those E1, E2 are the column of this matrix, right? So the this guy over here is a matrix which has yeah, has capital D, EDs, right? So these are the columns of this matrix. Tough. E1, E2, E3, E4, and so on. Each column has height of, like, each column is batch size in size, right? You following? Yes, no, you lost. Not everyone is shaking their head. I try again. So E is a matrix having height, capital B, which is the batch size, and width, capital D, which is the dimension of this vector. So these vectors are like first vector, second vector, third vector. These are the EB vectors, right? Each of these row vectors have size D. So each of these representations are D-dimensional representations. And they are stacked horizontally, right? Like rows. In this case here, I choose instead to represent with a lowercase d, each specific column, right? Of the thing. How many columns I have? D columns, right? So that's why there is a lowercase d. I have 1, 2, 3, yada, 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 until the last capital D. All right, so B is the batch size. D is the dimension of the embedding, which are row vectors. All right, one more thing. I have my E matrix, which is going to be my E matrix minus the average along the columns, right? And so I end up with a row vector, right? So I sum all these row vectors together, all the embeddings, and I divide them by the number I have, right? I have B, capital B, of these row vectors. I divide by number B, right? And I sum them all, right? So I have the average embedding. So this is the average embedding. I take my matrix, and I subtract to every row the average row. So these are my centered embedding. I just kill the DC, the continuous value, right? Okay, I know it's a little bit heavy, this slide. It's going to get heavier. All right, what's going on here, right? So forgetting about the fact that I divide by this stuff here, and I sum all, what is this stuff, right? So the thing in the parentheses is going to be the value of whatever is inside if it's positive. If it's negative, this stuff gives me 0, right? This is a ReLU. This just gives me the positive part. So what is that we are trying to do here? Here, I compute the square norm of this centered thing, right? What is the square norm of a centered vector? Question to you. Say again? Who talk? No one talk. You have a vector. You subtract from a vector its mean. And now you compute the square norm. What is that you are computing? The variance. Right? You take the vector, you subtract from the vector the mean, you compute the square length of this vector. Is it correct, right? I'm not crazy. Yes? All right, very good, right? So I take the vector which has been centered, right? And I compute the square norm. So I get the variance of that vector. The variance across the... What is the size of this guy? Batch, right? And so this is the variance across the batch, right? My phone, my watch tries to answer this question for you. Okay, awesome. All right. So here I compute the variance. I divide by blah, 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 whatever. Some epsilon for whatever stability. I take some square root, so I get the standard deviation. I get gamma minus standard deviation, which is going to be my variance term, okay, the V term. So as long as, when is going to be this term complaining? So this term goes to 0 as soon as it becomes negative, right? When does this thing becomes negative?
Square root is greater than gamma.
Right, so this is the standard deviation, right? As soon as the standard deviation grows larger than gamma, overall, this stuff goes to 0. When is this stuff going to be complaining? When is going to be very large, this term?
Zero variance.
What is the minimum value for this guy here? 0, right? So why do we need this term, right? So let's step back, because I think I started in the fifth gear without actually starting from the what are we trying to do, right? So what is the objective of the overall system? Do you remember? We have a representation for my input x, which is called ex, the embedding for the x. I have a embedding for the y, right? What do we try to do with these two embeddings? I should have put the s first, right? Too bad. Say again?
What?
Yes, we want to minimize s, but s, guess what is going to be s?
The distance.
The distance, right? So s is going to be the distance of these two representations. How do you make two representations close together?
Always to 0 or something.
Exactly, always to a constant value, either 0 or whatever, right? So if the model outputs 0, 0 is always close to 0, or 17 is going to be always close to 17. So the model will be very happy to just output a constant arbitrary number, right? Why not? And so you have a network outputting a constant number, regardless of what you put inside. Is this helpful? No, okay. Until here we are following. Very good, right? So the network is just whatever you input in the thing, you have all 0 matrices, and then it's 0. And it's 0 is equal to 0 all the time. Hey. Okay, not good, not good. Bad network. So what are we trying to do here? We said if the standard deviation is 0, so constant output, right? If the output is a constant value across the batch, this stuff will be 0. Overall, this stuff becomes gamma, right? More or less, something. And so this V is going to be the sum of all these gammas, right? Well, I divide by D, so the average gamma. How can I reduce this term? By increasing the standard deviation, right? So I can increase the variability of the output within the batch. So the network would like to output a constant value. Instead, I force the network to output within the batch different outputs, right? To have a variability across the batch. Very good, but definitely I should have put S before. You see, you prove the fact that I haven't tried to teach this stuff before, right? This is obvious, it's my mistake, right? Because it's logical, that it's missing parts of the explanation. Second one, it's so cute, but it's kind of scary too, right? So, all right, so what is this stuff? Do you know? Frobenius norm. What is the Frobenius norm? Do you know?
It's the norm of the polarization of the link.
Very good. Okay, you know already everything. I see. Yes, correct. So you take all elements, you say you square them, you sum them all, right? Okay, what is this? What is this item over here? Okay, yes. Okay, it's too easy, right, for you? Okay, I see. No, because I know. Okay, I want to see whether these people are following what I know. All right. So E0, no, E center, right, is the version of the E with the subtracted mean, right? And then I transpose it, right? So I have D times B, right? I multiply D times B times B times D, right? So I get a square matrix of size D by D, which is representing my, what is this matrix?
The distance of each element is a variance matrix with themselves.
You said you were not going to talk, right? Okay, someone was answering here.
Similar to a covariance matrix.
Covariance matrix. You actually get the covariance matrix because we divide by b minus 1, right? So you actually get the covariance, estimation of the covariance matrix, right? I sum all the squares, right? I do the same here. I take the diagonal and I remove all the diagonal, right? So basically this term over here is getting the covariance matrix. I sum everything but the diagonal, basically, okay? And this term is going to be complaining if my off-diagonal terms are large, right? Either negative, or very positive, but large, right? Because I squared them, so who cares about the sign? What does large covariance term mean in terms of correlation? I mean, what does having large off-diagonal term means in a covariance matrix? Tell me.
Variables are highly correlated.
Correct, right? So what does this term will try to do?
Measure the correlation overall
Minimize
batch.
the cost.
Right, but we are going to be minimizing this cost, right? And so we're going to be trying to minimize the correlation of the different dimensions. So we try to come up with representations which have the most informative type of description of the input, right? Why is this important? Guess what? When we try to make this thing equal to each other, we said that a constant output could be just working. Okay, a little bit harder, or well, still easy to predict, but easier to predict than the, I mean, just zero is going to be the easiest thing. Something a bit less easier to predict, which still make this happy, is going to have each vector being a constant vector, but different from each other, right? So each vector could be a constant vector, but all of these vectors in the batch are different from each other. This term says no, you cannot have constant vectors. Each vector has to be the most informative as possible, right? Okay? Awesome. And the third part, which of course should have come to the top, right? So tomorrow this stuff goes up before going online, right? S, right? The S stays for S. I forgot the word. Similitude, right? Similarity, there you go. The similarity term measures how similar EX and BX are, right? So I take each of these representation, I subtract the one to the other, and I square, right? And I check what is the square distance between the two things. So the similarity is simply the squared Euclidean distance between the two. This V term complains if the variance, or if the standard deviation is not gamma at least, right? If it's lower than gamma, this stuff screams. This stuff screams if the cross terms are going to be correlated. Finish, works. Okay, so there are no other magical aqua boxes as you have seen in all the other type of things. This stuff is called VCREG. VCREG means variance, invariance, and covariance regularization. Each block, it's a regularization block, right? So this is a regularization term, this is a regularization term, regularization term, regularization term. The invariance term is the S, trying to make the two representations similar to each other. Check the paper also for the description of all the other techniques, right? Again, there are many of these joint embedding methods. I think it's a bit pointless to go over the others which are more complicated and to explain, right? It's pointless. If you understand how this works, well, all the other things are just a bit more complex, right? Which is unnecessary. Okay, so this was the first part I wanted to talk about. And now you can choose, I think, what you want me to talk. Oh, next, but there is one more thing, right? What happened? Oh, here there is a box, right? So we said this is an energy-based model, right? So I have my capital F. And what is F equal to? We already know, right? Tell me. Talk back. Cannot hear you. Yeah, that one. Okay? So the F is going to be simply the summation of all these terms. Very good. Okay, awesome. All right, as I was saying before, we are done with this first survey of the state of the art of this self-supervised learning thing. Let me actually switch to full camera. All right. So we are done with this first part. There are two options for the second part, right? I think I cannot make three parts, otherwise we are here for dinner, right? So you should tell me what you'd like to hear from me. Either I can give you an actual lecture on the EBM with the ellipse we saw before, right? So I can tell you how this one was trained, right? And basically, I explained to you this argmin for finding the y and so on, right? Or we can talk about a bit more about this architecture, LVGEBM, right? So I talk about this one a little bit, right? There are a few of these ones here, which are I showed you just before, right? This one were the options, right? We have denoising, autoencoder. We may have the GAN, actually, which is an energy-based model. We may have a contractive and variational and sparse autoencoder, right? So either I can give you a few examples of generative, latent variable generative energy-based model. So it's a bit more technical, and this is not going to be, you already should know how this energy-based model works. Or the other lecture is going to be a more beginner-friendly energy introduction lecture. What do you want? Hands up. Hands up for, so first, you want the beginner-friendly introduction to energy-based model, learning how to produce a ellipse, which is this one. So hands up now for the introduction. Okay. Hands up instead for those who would like to learn about GANs, energy GANs, denoising autoencoder, contractive and variational autoencoder. Okay. Yes.
I think we also have people from the bachelor, it might be more interesting.
The lecture one, right? Okay. So I guess you're gonna hear now from me about the thing actually I prepared this morning for you. And I actually refurbished the slides. So this is gonna be a lecture, unless you want to take a 10 minutes break before this third part. Make like that if you wanna take a break. Okay. So let's take a break of 10 minutes and let's come back at 7 minutes, right? Let's come back at 25, where we start with this energy-based lecture. It's going to be beginner friendly, okay? What's up?
I have a question.
Yeah.
Actually, I'll start with that. You said before that you can use jam model as a 0.9, so it's a sort of initial presentation. If I understand the principle, I don't understand, for example, in practice, how would you do it, let's say, image recognition?
Yeah.
So how would you, even like a high-level explanation, how would it work? So how would you do it?
Right. So this is how these models are actually evaluated, right? So if you check the latest paper, right, and this one, the paper I show you here, they use different notation, worse notation. Okay, if you check this paper over here, they show you how they evaluate all the models I showed you before. This one and this one, they are all evaluated and compared on the downstream task, which is basically you go here, you take this model over here, you insert a linear classifier, and you try to learn the what is the identity of this image, only training a linear classifier. or a few layers, multi-layer fully connected network here. You just train this is supervised learning, right? So basically, after you extract this stuff here, your Y is going to be your label, and then you just get your decoder to produce the correct class output for that specific image. And so you just, let's say you just train one module. You remove the previous one and you just reuse this pre-trained model. So just instead of whenever you perform like supervised learning, you have to start with a model. And the weights you are going to be starting with are automatically generated by PyTorch, TensorFlow, or anything, right? Instead of using random values, you're going to be using a model that has been already trained with these techniques, such that the parameters you're starting with are already suboptimal for your specific downstream task.
Okay, but there will be layers again with the same problem of initialization, is it?
Second, sorry?
That there will be some other parameters of the model which are not initialized.
Correct, yes. So I will take just this guy over here.
Okay.
I will pop up a couple of layers of fully connected model, and I just train those few layers. Those will be like 1,000 parameters, 10,000 parameters. I can train with few samples. This stuff is hundreds of millions parameters. In order to train hundreds of millions of parameters, you need a lot of labels. The few parameters you're going to add, 1,000 more, doesn't really cost you that much to train. Just a few samples are going to be sufficient in order to be correctly classified the input, given that your encoder is already disentangling the input manifold. Okay, does it make sense?
Those are fixed, so then the encoder will be fixed. During the training
You
phase.
can either keep it fixed, or you can do so. This called you can freeze the weights, or you can do something called what's called fine tuning. Fine tuning means you have a lower learning rate, and don't forget to add an additional cost for the parameters to the initialization. So you have these initial values or the parameters, it's a value specific. Then you want to add, you want to train your model while having a box between these parameters and the initial parameters, such that you perform a regularized supervised learning. Meaning, this is the random value for the parameters. This is the parameters you got from self-supervised learning. Add a spring, each box is a spring, right? Add a spring to that one, such that when you find a solution, you don't go too far from where actually you initialize, because you spend so much time and effort to get that initial location.
Okay. No, I'm just getting confused, because now you're pointing on the Y side.
Yeah.
But not necessarily the Y will adjust it, because the task might be different, so the Y might be different. The input data will be the same.
And this is the third time I'm showing this slide, but it's no, that's totally fine. But I understand that this is your data.
Sure.
These are all images. Left side of the image, right side of the image. Previous part of the text, second part of the text. When I try to predict the Y from the X, everything lives in the same domain. Everything is an image. I try to predict the next frames of video from previous frames of a video. If I would like to...
I understand that.
Ah.
My point was that when you do this thing to, let's say, optimize the representation of X, if I'm getting...
No.
No?
That's the point. What I care is the representation of the Y. Next lesson, after the break, I'm going to tell you about this. Okay? So X is what I observe, and I don't want to predict. I don't care. Y is what I want to predict. I observe during training, such that I can connect it to my X. I have my X, and I try to predict my Y. During inference, I would like to only produce Y. I don't have Y. I only have X. So I never care about X. Okay? So X, we don't care. I give you X. X is given. All you want to learn is the blue guy. next lesson, you're going to be learning everything about this. If it's not still clear after this, the thing, then complain. And 7 minutes break. I guess we come back at 35, okay?
Non mi aspettavo una cosa così lunga.
Me neither. Anch'io.
Devo scappare.
Oh, ok.
Devo scappare.
Aspetta che blocco qua il microfono, un secondo. All right. So back, here we go. So here we're gonna have these. You asked for it, right? So I'm gonna be just, let's say in English, I don't know, address your desires, right? And then give you this kind of. Don't worry. So I'm gonna give you this kind of introductory lecture on energy-based model. Again, this is actually from my class at NYU. So and also is also recorded on YouTube. So. Yeah, so this is like for master students usually, and also some undergraduates usually take this class. Anyway, we're going to be learning in the first part of this talk about how to perform inference for latent variable energy-based models, EBMs, okay? This is a toy example, an ellipse. Again, this is just for you to understand what is X, what is Y, what is Z, how the things work. And yeah, how all these models can be used for doing anything useful, okay? Microphone is on, yes, you can hear me, everything is all right. People from home, there's some spam, but otherwise I think it should be okay. All right, let's move on. So inference, right? We're gonna be talking about, in the first part, about unsupervised learning, okay? The unconditional case. Addressing a red shirt guy, unconditional means I don't have the observation, okay? I just have the why. I always try to learn the why. So this is actually something, usually all the books get it wrong. Sometimes you have like, you try to estimate the probability of y given x, right? Whenever you do some sort of like supervised learning. And then they say, oh, unsupervised learning is gonna be the probability of the x, right? No, we don't have this, right? We either have this one or we have this P of y. So either it's y and we don't observe anything, so unobserved, unsupervised, unconditional, or it's y given we observe something, okay? But we always want to learn about why. Why is my target? Why is the thing I want to model? Most of the books get this completely wrong. And they talk about P of x, which is the generative model. No, this is my generative model, okay? Again, semantics. So we start with the training sample, right? The things where we want to have, what do we want to have are the training samples. How do we want to have our energy? Our energy should be low, right? Because we want to find the solution of this. When we perform the inference, we're going to perform the argmin. All right. So I have these blue ball y's, which are going to be rho 1 function of x times the cosine of theta plus some noise, and then rho 2 of x times the sine of theta plus some noise. Rho is a function that goes from r to r squared, so goes from a line to a plane, and basically maps x into alpha x plus beta 1 minus x, and then beta x plus alpha 1 minus x. Everything is multiplied by an exponential of 2x. In this case, I have alpha is going to be 1.5, and beta it's equal 2, okay? So this alpha here is going to be 1.5, and beta is going to be 2. And my x is a uniform from 0 to 1, right? So when we start with x equals 0, the first component is going to be beta, right? So the first x is going to be 2, right? So when we start at x equals 0, my horizontal axis is going to be of the ellipse equal 2. And the vertical axis is going to be 0, it's going to be 1, it's going to be 1.5, right? So you're going to have an ellipse of width, this stuff goes to 1, right? For x equals 0. So you have 2, 1.5. And then as x moves to 1, you're going to have the x of 2. And then this stuff goes away. So the horizontal component becomes the shorter one. And the vertical component becomes the longer part, right? And so we started from the horizontal ellipse. And then we go to the vertical ellipse, also growing exponentially. So we go from a small one to whoop, large, right? Anyway, theta instead is my missing variable, is my latent variable. is going to be uniformly sampled between 0 and 2 pi. All right, so epsilon is simply some noise. So this is how my training point look like. Okay, the color represent the x. You're going to have the purple on the left hand side, and then the right for x equals 0 is going to be purple. For x equal 1, you're going to have the red color. You have that we start with a horizontal ellipse, as I told you, and we end up with the vertical red ellipse. Okay, so this is my training point, which are sampled again uniformly. So far, all right. Okay, but I have an x and I have a y, so this is a conditional case. But I said we're going to be starting with a unconditional case. So I basically say, oh, x equals 0. And so automatically the rho 1 is a constant equal to 2, and rho 2 is a constant equal to 1.5. Right? So we just start with infinitely many y's, right? We would like to learn infinitely many y's. But then I decide to just sample 24 different y's from this data generation process. So those are my 24 points, y1, y2, y3, so on. So those are my observations. What we will try to do is going to be having this energy, which has a low energy for these points, high otherwise. And here we go. These are my data points, 24 points. x1 coordinate, x2 coordinate. All right. Untrained model manifold. So we start with this latent. Pay attention, this latent now is no longer bold. Before we had a bold orange Z. Do you know, can you guess why it's no longer bold? Do you know the distinction between bold variables and non-bold variables? It's a scalar. Yeah, so Z actually lives on a line. It's a single dimension. So Z is going to be a continuously, well, it actually is like, discrete in this case. For the sake of visualization, it goes from 0 to 2 pi excluded, with jumps of pi over 24. So how many points do I have there to play with? 48 points I will play with, okay? But anyway, Z we had to think about, it actually moves continuously, right? Up and down that line. It goes from 0 to 2 pi. Then this stuff goes inside a decoder, and then we're going to be producing a violet bold Y tilde, which now will enforce to be living on this closed manifold. On the bottom side, I have my target, my blue bold Y. And then Papa is speaking, but okay. All right, so on the bottom side, we had the blue bold Y. And this is my untrained model manifold, okay? So these are my 48 points that I sample from the model when the model is not trained, okay? This is an untrained model which is producing this result. Are these good results or bad results? How can you describe them? Oh, there is a question from home. Okay, that was a previous question. Okay. Is this a good energy model or a bad energy model? Well, you don't even know if it's an energy model. There's no energy right now. Is this a good model or a bad model? I cannot hear you.
Bad.
It's bad model. Why is it bad model? Say again?
It's different from the ellipse.
Correct, right? These points I sample from, the 48 points I sample from my model, don't barely go close to this point, right? Maybe this point, but somehow, but these are very far. And so this is a bad model. This model is definitely untrained, right? But who cares? We're going to be talking about inference first. Then we're going to be learning how to adjust the parameters such that this model will match the target, the blue bold Y's. All right. So, what's happening? Oh, energy function. So again, we're gonna have this spring term, no, this cost, which is gonna be measuring the distance between my violet y bold tilde and my target, right? And then I have here that this one here is gonna be my square Euclidean distance between my target and my predictions. As I said before, we can just put a box around everything. That's gonna be my energy, E. And so here we have my energy of y and z. There is no x, right? Remember? X is given. X is fixed. It's one value. So this model doesn't have an input. Do you see this point, right? This model doesn't have an input. This model only produces a energy as output. The inputs are going to be this target that I provided to the model. And then I have this free variable, which again is not given, it's missing. All right, so we said that the C is going to be the squared Euclidean distance, and then my energy is going to be equal to the box, because there is only one box, otherwise I sum all the terms. So, even digging more further into this thing, right? If you perform the square Euclidean distance, it's going to be simply summing up the components, individual components. And what are the individual components? Where are the first item? Okay, I should have flipped the other one, right? It's going to be the y minus, doesn't matter, it's squared. So it's going to be the first component minus the second component. First component minus first component squared. So here you go. Plus second component minus the other second component squared. For every possible point, blue ball y in this collection. How many do I have? Do you remember? 24. Very good. So I have 24 samples. Therefore, how many energies do I have? Do you see? How many values can this take? I have 24 possible functions of z. Z is a continuous variable, but I can index each of these energies with the same index as the y. So I have right now 24 distinct energy functions, one per each sample in my training set. Okay, all right, very good. What's inside G? Right, so G is a function that has two components, G1 and G2. It's a vector column, right? Column vector. And it maps my scalar input Z into W1 cosine of Z and W2 sine of Z. Question, how many parameters does this model have? 2. So you have a deep network, it's not deep network, it's 2 parameters. Okay, I have 2 parameters which are representing what? If you don't have W1 and W2, what is this stuff? Cos Z, sine Z. Yes, it's correct. You had to shout because I cannot hear you otherwise. It's a circle, yes, a circumference, yeah. But if I change the 2 different terms, what do I get? I get the ellipse, right? So I get the possibility of changing the 2 axes, yeah. Awesome. And so now you can see how a scalar value as the input here allows me to generate a curved output there, okay? So I change possibly from 0 to 2 pi continuously, and on the other side I go around this ellipse, well, one time, right? And I'm gonna just put it there for later, for convenience, that E of Y and Z, blue bold Y and then orange Z, okay? Question so far? You can see this is slower than the type of before of the lecture, right? Of the survey, right? Yeah, what's up?
But we're choosing a model for G.
I choose a model for G.
It looks like we already know the nature.
Correct. This is let's read together the first slide. No, the previous slide. Very good. Very good, very good.
So I don't know if we got the question right. So the assumptions that we know that it's an ellipse, and we have just defined which one. Is that correct?
So we know it's an ellipse. Yeah. So let me show you. So we definitely. Oh, what's happening? There we go. So we definitely know we are trying to learn an ellipse, but we don't know which one. Yes.
Okay, so that's
And it's centering 0. And so this one you just saw right now. Okay. Other questions? That was an okay question. I already got this question multiple times, but it's a toy example just to understand what E is, what Y is, what Z is, what all these things are. So the more clear the example, the more down onto earth, the more we can actually understand everything that's going on.
What's not clear to me is...
Say again?
What is not clear to me is we have 24 points.
Correct.
And we have just a scalar. Is that correct?
This is a scalar, yeah.
So that is going to generate a point in the ellipse, I reckon, one single scalar. And
so far, this is going to be a function.
Yep.
This is a function, and I have 24 different functions. One function per y.
Okay, but I mean, depending on the z you choose, you might end up in the right point.
Next slide.
Okay, sorry.
No, don't worry. But the point here is that I have a function. So it should be a function of 2 variables, but since this is discrete, then I can tell you I have 24 functions, right? Otherwise it should be like a more dimensional function, whatever, right? It's a continuous, right? But not continuous. You know, a vector is the same as a function. A function is a vector with infinitely many items, right? No need for regularizer on Z here, but if we make Z 2D, we should add any regularizer. That's correct, Assem. So in this case, Z doesn't have its own box because Z is constrained to be living on one line. So we are choosing right now an architectural type of energy-based model. The regularization is implicit in the choice of dimensions for Z. If Z would be 2-dimensional, you understand now that this model can produce every possible value, right? But we haven't talked about how we do anything. So yes, I answered to the question online. We would have needed a regularization term in case Z was more than 1 dimension. Questions? You still awake? Everyone? All right. Okay, so let's have a look to these 24 different functions, right? So here we go. Oh, it took forever to draw this stuff. Come on. Just give me some satisfaction. Anyway, what I'm showing here is going to be, given that I pick out of my 24, my y I pick is going to be the first one, then I end up with this type of function. This is going to be my E1. Okay, so I address the energy with the same index of the sample. Down the row, on the 6, when I pick the 6th sample, I'm going to have the E6, right? Same when I get down to the 19th sample, I'm going to have the E19. And then finally, when I pick the 24th example, I'm going to have my E24. So I have 24 different energies. Energy functions of Z. Correct. So here on the abscissa, you have Z equal from 0 to 2 pi, right? These are the extrema. Yeah, what's up?
In this case, the parameters W1, W2 are fixed.
Like when you start with an untrained model, yes, those are fixed parameters, which are definitely not correct. And these are what my energies for this untrained model look like. And here we go from 0 to 12. So we can pay attention. There are 2 major different types of energy. there is the nice convex looking smooth U shape, and then there is like Jan signature. Okay, you don't know, but he signs like that. Okay, so you can tell this is not convex, right? Also, this thing, I'm not sure it's convex because you can shift it, right? This is connected to this point. But anyway, you can see there is one global minima. The other one has two minima. What am I visualizing here? What are these curves? Do you remember? How do I compute this red value?
Y and values axis. Not the point that are met by the z. By the z.
Yeah, which are the point mapped by the z, the z?
The tilde, no.
Y tilde, right? Which are coming out from that cosine and sine, right? So we had the y given point minus the g1, and g1 was the w1, the cosine of the z, and then the other term was y2, w2 minus y2 minus w2 sine of z, right? And z varies from 0 to 2 pi, and so we end up with all these squiggly lines, right? And so we then focus on those two. Let's start with the U shape, right? Which is going to be less painful to play with, right? All right, so we said it goes from 0 to 2 pi, 0 to 12. And so here we start, right? So I'm asking you, what is 12? Which is where? Tell me where to go.
So you have to tell me which point is which, because otherwise I don't know.
So the x, green x, is going to be my chosen x, my chosen y, right? Okay. This is my picked y.
Okay.
And then as I change z, I move around this thing. Okay, so I'm asking you, what is 12?
Minus 1.5.
This one? Okay, so how much is this point far from this point over here?
3.5.
1, 2, 3, 3.5. How much is 3.5 squared? 12, correct. Very good. Okay, so the energy is the square distance between my given chosen point, the green x here, and every point on this generated output when I change the latent. Right? What is the height of this point over here? Question for you. 0.25, right? Correct. Right? Which is the 0.5 square, right? Nice. Okay, awesome. Very good. So next one. Let's go for the squiggly line. So now we're going to be understanding why on earth this stuff is no longer convex, right? So what happened here? What is this height over here? The lowest height. Who's talking?
1.5, sorry, one.
No, you're talking. You know already all the answers. Someone that doesn't know the answer, like first guy here, mask. Well, everyone has a mask. Gray shirt. What is the height of this lowest point? You can ask the height from the next neighbor. Anyone in the team there? No, you don't give anything. Anyone, like you are 5 people there, you can talk to each other.
Try.
Huh?
Please try. Come on. You're so bad.
Adesso puoi rispondere.
All right, so what are we trying to do?
Distance one?
We are trying to compute the distance to this point, right?
Yeah.
Which one is the closest point to this one? This one? Is this one the closest point? Is this one? Is this one? Is this one? Is this one? Which one is the closest point? This one. How far is this?
More or less one.
This would be 1. 1.1.
Okay.
But then we have to take the... How much is 1.1 square? 1.2. Anyway, so this height here is 1.2. Why there is another minima here? Where is this point? So let's write down, right? 1.2. We said we have 1.2. What is the height of this other minima here? How much is this point?
I think it's 3.8.
So you have 0, 5, 1, 1.5, 1.8, right? How much is 1.8 square? Calculators, come on, you all have mobile phones.
3.6.
3.6.
Can we just call it 1.8
It's
squared?
less,
No, because we want to compare
less than 4.
1.8 to 324.
3.24.
Okay, awesome. Then how much is, which one is the maxima? Is this, which one is the highest maximum? This one or this one? Okay, so how much is the highest one?
3 squared plus 3 squared.
Here, right? So this is 1.5 times square root of 2, right? But then we had to take the square. So 1.5 times 2. We have 1.5 times square root of 2, right? But then we had to take the square. So 1.5 times 2 is 3. 3 times 1.5, 4.5, right? Finally, what is this lower maxima here? Which is going to be something less, right? It's going to be 1 point, maybe, I don't know, 4 times square root of 2 square, right? So something less. Let's say, okay, can we actually find what is 1 point, we said 4 square times 2, 3.9. Okay? Hello, come back to me. All right, so we found out all these points. Question for you. Now it's going to be a very interesting question. How much is W1 and W2? Tell me W1. What are the options? What do you think it could be?
1.5.
Someone said 1.5. So hands up, who thinks it's 1.5? Yeah, one person, 2 people. Okay. How much is it instead?
Should it be true?
Say again, sorry?
Shouldn't it be true?
Shouldn't it be true?
True.
True. No. So you are checking the extension of the purple.
What it should be, okay. What is it now?
Right. And someone said it's 1.5, which is this length, right?
Okay.
Which could be right, but it's wrong. Because check this curve, right? Where do we start in this curve? We start for z equals 0, right? Z equals 0, what is the height of this curve? Which one? For z equals 0, what is the height of the red curve?
4.5.
No, it wasn't 3.9.
Oh my God, what's going on? Right, so these are the 4 interesting points, right? We have one maximum, second maximum, we have a minimum, another minimum, right? So we have 4 points. These are the 4 values for the height of that curve. I'm asking, what is the height of the curve for z equals 0? 4.5. So where are we for z equals 0? What location are we? On the left-hand side. So how much is going to be W1 right now? If you are starting here, cosine of 0 is going to be plus 1, right? But I am at, oh, how much is W1? Oh, very good, very good, very good. So this is minus 1.5. Very good, very good. Okay. Then in what direction I'm moving? Am I going upward or am I going downward? Where am I going to? We're going upwards. And so how much is W2?
Is 0.7.
Wait, what?
0.4.
0.4, very good. Plus 0.4, very good. See, so this is the level of detail we go through in order to understand what's going on here, right? But now you understand what these figures take, because guess what? This took an hour to draw, right? So I spent an hour, you're, getting the pain. Alright, awesome. There is one more of these things. Anyway, moving on. Free energy. So, okay. Remember, what is this free energy, right? Let's figure out. So this free energy, I'm just computing the minimum value of the energy with respect to the latent. What does it mean? So we can also get Z check. Why is it blue Z check? Because it's cold. Why is it cold? Because it is a low energy value, right? Why there is a checkpoint downwards, right? So it's low energy value. Okay. And you can do, if it's discrete, you can do exhaustive search, conjugate gradient, line search, LBFGS. Okay, you can do many things. You don't care. So my free energy is going to be the energy at the value that is minimizing the energy, right? Of course, the same thing, right? This is the arg minimizer. You put the arg minimizer in the function, you get a minimum. All right, so this is my function. I just make it a bit larger so you can see everything. I start with an initial guess for my z. Then I perform gradient descent. And I get my z check, my minimizer. And finally, I can compute what is my free energy. It's blue because it's cold too. Okay? Here, everything? Very good. All right. Next. What does it mean, this in the input space, right? So again, addressing your question, we only have y's here. We don't have x's, right? All we are playing with and all we are learning about is y's. We don't even have x's right now. Anyway, so the point is that here we have many, many possible y's that can exist. So our model has to be able to produce many, many possible outcomes. All right, so we started with our initial guess in the drawing. That's my z. This is the generated version of the z tilde, right? So it's going to be my y tilde if you want. Then I perform gradient descent, and I get to this point, and this is the g of z check, right? This is the generated version of the minimizer for the minimizing latent. And then how much is going to be my energy here? The same as before, right? You can tell me. Very good. All right. Next one. We go with a U shape. Same thing. I may start in this location here with my initial guess. I perform gradient descent. I go down here. What is this thing? I just draw it there. Again, free energy, lowest value of the energy. Again, so same thing. I have my initial guess. I go down with stochastic gradient descent. I get my final 0.25. Okay. So what next? Oh. How many energies did I have before? 24, right? Because I had 24 points. Now I'm going to take every point in the plane. And then for every point in the plane, you have every point, every possible function. But then I can minimize it, right? And so I can find for every point a free energy, right? For every point I have one free energy. And so I'm going to be focusing on these specific values later on, okay? So what is the free energy for this one here? Can you tell me? The same exercise we have done so far. What is the free energy for this guy? Free energy is going to be the, tell me. The minimum value of the energy. What is the energy? The energy is the square distance between this point and every possible point, right? Which one is the shortest one, minimum one? This one, right? So what is going to be the free energy for this point? I guess 1.5 squared, right? 4.5. Same for this one, something here. Same for this one, something here. Same for this one, something here. Same for this one, something there, right? And so these are the energies for each of these 5 points, okay? With the minimizer represented with the x, corresponding x. All right, so let me show you now the free energy for every point in this chart over here, okay? So what is the free energy again? Repeat. Free energy is the lowest value that the energy can take, right? So it's 1 point for 1 point. So each of these points, I'm going to compute that value. Right, so I'm going to show you values. They go basically from 0 to 2. When am I going to get a 0? When we are on top of the manifold, right? When are we going to be far? When we are far from the manifold. Very good. So we start from f infinity 0. We go up to f equal 1, up to larger than 2. And so this is how the free energy look. Around my purple ellipse, my free energy is 0. Away from the loop, everything is higher, right? And also here is a bit brighter than here. Okay? And these arrows are basically the location. Tells me where is the location of my arc minimizer, right? So my arc minimizer is something here, arc minimizer is something here. Here is actually in the point, so there is a point. Otherwise, they tell me where my arc minimizer is. Question again, is this a good or a bad model? Bad. Why is it bad?
Because most of the points lie on high energy.
Right, so my blue points, which are the points where we were expecting to have a low energy, are high energy. And points that are not supposed to be low energy are low energy. It's broken, this stuff, right? We haven't yet trained, so let me also show you a little bit more nicer thing with more nice color. Like, so we go from a blue for 0.5 is going to be a white, and red is going to be larger than 1. And here we're going to have some surface levels, okay? So here you can see clearly this model, which goes at 0 in the central part, and then it grows in the center, and then also grows on the outside. These are, again, all the curves that have the same color, right? So each of these lines have the same color, it's surface levels. Okay? So what do we need to do? A bit enlarge this thing and a bit make it a bit, well, taller, a bit larger, right? Very good. Questions so far? Are you still following? Are you following? It's easier than the first part. Yes. You like it? Okay. So we have like 15 minutes more, and then I'll let you go. So you're gonna be free from thinking and be, getting crazy here. All right. Let me chop off the thing for a specific value. Like let me chop that bathtub such that I choose y1 equals 0. So I cut it half, such that you can see how this thing goes up over there. What is the thing on the left hand side of 0? What is this shape? What is it? What is this function that you see going from minus whatever infinity to 0?
So what sort of function?
What sort of function is this? Why is it a parabola?
Because there's the square.
It's a square, it's correct, yes, very good. But then why this parabola goes up and then it goes down again?
Actually?
Obviously, you reach the point that you're minimizing to.
Correct, right? So because we always look at the closer point. So until we reach the center, we are closest to one point. As we pass the center, then we're going to be closer to the other point, and we go down the other parabola. Very good. So there is a bump in the center. All right, what's next? Oh, yeah, so how can we compute this free energy, right? So before, I just show you that the free energy, infinity, so this is the 0 temperature limit free energy, which means 0 temperature or the beta, which is the coldness, goes to plus infinity. That's the thing here. That was the mean. Otherwise, we're going to be talking about this F beta, which is going to be this marginalization of the energy. Again, I don't care to be talking too much about that. Beta is going to be my coldness. Again, if you're a physicist, you can see this as the inverse Boltzmann. The K from Boltzmann over the constant, Boltzmann constant times the temperature, right? So that's the inverse temperature that comes from the whatever physics, right? We know this stuff. Let me skip a little bit ahead. Yada, yada, yada. That's what I showed you before. So this F beta, it's the soft minimum of the energy, okay? Either it's the minimum, if you take this limit for the beta that goes to plus infinity, super cold, or if you warm it up, so beta is the coldness. Larger the beta, the colder the thing is. The lowest the beta, the warmer it's getting warm, right? So if it's super cold, you're gonna get the minimum. If you relax it, you increase the temperature, you're gonna get this soft minimum, which is this something, okay? We don't care. Well, we care. It's gonna be the summation of all the exponentials with a negative sign for the energy. And then there is a log of the sum of the things, right? So the log of the sum of the exponential of the negative energy, right? Without negative in front. Whatever. I mean, it's just showing you that if you compute the limit for beta that goes to 0, super warm, this stuff becomes the average. So if you increase the temperature and this stuff really gets warm, you kill all the latent, and then the latent will all contribute to the exact same amount, killing the whole point, killing the whole system, right? But again.
Sorry, Alfredo, if I understood correctly, that is just the case of we had before the ellipsoid, and we always predict the origin.
Correct. Okay. So if beta is not 0, meaning it's not super hot, one specific latent will be predominant, which will try to encode that specific case. If it's super warm, then all the latent will try to predict all the cases, which is exactly the same as not having latent, right? But again, this is becoming a little bit too detailed. Free energy. All right, so we have back the U shape, right? The nice, easy one. We had that diagram. Remember, we were going down this way, and we were computing that square thing. We have the definition there for the free energy, which is the marginalization of the latent. We choose beta to be 1, such that we can just remove it from the equation. And here we have the first diagram. You have to tell me what it is. So this yellow point, it's 0.75. What is it? Can you guess?
Exponential. exponential
Yeah,
distance.
it's the exponential of beta is equal to 1, right? So beta doesn't exist. So what is 0.75? Exp of negative. How much is this? Can you compute with a calculator? Exp of negative 0.25. Anyone? Is someone trying at least? Or are we just waiting for Santa Claus? 0.77, right? Which is roughly what I show you right over here. So this point over here, the latent corresponding to this point, will contribute to this summation with a 0.77 term. How about a latent down here? What is the energy of this latent? No, the energy. The energy of this latent.
The energy is 12. Yeah.
12, right? What is e to the minus 12? 0. Okay? So this latent here will not contribute for my free energy. This latent here will be the maximum contributor for 7.7. All these guys over here are somehow contributing by 0.7. These guys over here contribute something between 0.5 and 0.6. These guys contribute something between 0.2 to 0.4. That's it. So before you saw that my free energy was defined as being the minimum, which means
1 point.
1 point. One latent tells you what the free energy is, right? One latent, one free energy. Here instead, a multitude of latents that are somehow close to the actual correct solution will contribute to the final solution, okay? So this is a possible way to combat overfitting. The other thing you may have, like I think about this as a porcupine. You have every spike that can be the closest, right? So you have 1 point, you have this point, this point, this point. So every latent can be individually trying to give you to be connected to one sample, right? One latent, one sample. This one, you have that multiple latent will contribute to the final free energy. And this is again a marginalization. I mean, you can think about this stuff as one is the minimizer, the other is like the Bayesian approach, right? Some sort of thing. Anyway, so this was, you got it right. Guess what happens now if we have the squiggly line, right? Where we were, what happened? My God. Where we have this double minima, right? So we end up with this location. These points over here will contribute for 0.25 in the summation, right? And neither this second minima doesn't do anything, right? Only these points over here. Even these ones are too far away. So nothing contributes. Okay. Very good. What happens now if I choose y not to be the center? How are going to be my energies distributed, my contributions for that integral? Remember? So this is my model, right? I choose the green point to be in the center. What do you expect to see?
Equal contribution from the two parts.
A little bit of yellow here,
Yeah.
purple and purple, right? And so here we go. Okay. So the free energy of this point will be higher or lower of this one. This one, right? Okay, this point, free energy, this is a S, right, for summation. It's a summation of all these contribution. Because the contribution are these yellow things, right? So there are a few yellow things of height 0.7. In the other case, I have many more yellow contribution of height 0.85. So what is the free energy of this point compared to the free energy of this point? Can you tell me?
The one in the origin is a lot higher.
Which one is higher?
The one in the origin.
Correct, right? So this point, we expect to have a lower energy than this point over here, right?
Sorry.
Yeah, what's up?
If it's true that it looks like, are they also more concentrated on the corner than amber point? Is it?
Yeah, but if you count it,
But also the absolute value inside.
Okay.
it's 0.75, right? And I count 1, 2, 3, 4, 5 at 0.75.
Decided, and the absolute value.
The other one I count 1, 2, 3, 4, 5, 6 at 0.9.
Yeah.
Right? So there are more, they are definitely higher. All right, so training. How we saw this stuff, there was the inference. Now 5 minutes, we learn how to train this model. What does training mean? Sure, but despite the thing I wrote on the screen. The same question I asked you before. What does training mean? Finding parameters, very good. All right, let's figure out how to do that. So we have to use, what is a typo? A loss functional. What is a functional? A function that gives you a scalar, given that you feed it a function, right? So a functional actually gets a function as an input and tells you a value, a scalar value. So my loss, my batch loss functional is going to be the average of this per sample loss functional, the same as we have seen in all other classes. But the point is that the input to this thing here is a function. So this is a scoring function, null, for a function. It's not a loss function, because a loss function tells you how good your parameters are. A loss function null is telling you how good your energy function is. Huh? Okay. So the simplest type of energy functional, given a free energy function and the point, is actually the value of that function at that point. Okay, that's very straightforward. So the actual value of your free energy is the free energy at that location. We're going to use that one. There are other options, as I told you in the first part of the lesson. We can have contrastive samples. And then my loss is going to be the positive part of M minus the bad guy minus good guy. So what does this tell us? This wants to have the bad guy higher than the good guy, at least of margin M. You see? Okay, good. Finally, this is exactly the same as before, but smooth version, right? The log of 1 plus x is a positive part with a smooth edge. We're going to be using this one. So we're going to be choosing our loss function null to be the energy function at the point we are looking at. Okay, again, we are choosing to use the energy function null to be the energy function evaluated at the location blue ball y, right? Blue because it's called low energy. Red because it's hot. Hot because it's pointing up. Very good. All right. First one, 0 temperature limit, the one that we chose the just single point, right? Untrained version, the one I show you today. So this is the thing I show you today. What are these arrows, right? So what are we trying to do? So I have this point. What is the free energy?
It's the closest.
It's the closest point, which is this one. And then what I try to do I try to minimize the Euclidean distance. So what is the gradient of the Euclidean distance?
This case is the connecting line.
The connecting line, that's what's written here, exactly perfect. So I have this arrow, which is my gradient. Almost. We see in a second why I tell you it's almost. Anyway, so this point somehow is proportional to the distance, right? And if I want to minimize, I have to move this point down this way until I hit this location. Very good. In this case, instead, is the train version. I successfully got each of these points, which are the individual single latent that are minimizing the energy function, giving me the free energy. They reach each of their own relative targets. Eureka, right? We succeed. We found W1 and W2 such that my continuous manifold, the one coming out from changing every possible value of Z, is matching my training manifold, the 24 points. Second one. Warmer. I lower the beta. It's a bit warmer. What's that? Questions? Okay. Don't get scared. Warmer, right? What's happening here? There are multiple latents contributing for the given y I pick. I compute the gradient. So how do I compute the free energy? Free energy is going to be the negative log of the sum of the exps of the negative energy. I take the derivative of that thing. What do you get? Log of the exps, you have negative log of the sum of the exp of the negative thing. I take the derivative with respect to the y, right? What do you get? What's happened to this stuff? Come on.
Minus 1 over, step by step. Okay. The sum of the x equals the sum, and you have x stays x, there's a minus which goes out, and then the derivative of b.
Which is?
I can't remember what it's e.
Yes, minus x. Minus x, minus.
Come on, you finish almost. What is the derivative of
Oh,
e?
yes, e is the distance.
Thank you.
Sorry, so the distance is square, so it's 2.
Right?
There is a 2 somewhere.
Sure, I guess, yeah.
Okay, some scalar. Okay.
Sure, I don't care. Very good. Okay? So, this is my gradient, which is proportional to the distance. It's missing something, right? Yeah, it's missing that one, right? There you go. Okay? So we have this arrow, the arrow that we had before, but now this one is scaled by this thing over here. What is this stuff? Ouch. Yes, that in everyone lingo, it's called softmax. In my class, we call it something else. Because the softmax was this one. Right? This is a softer max. So what is the derivative of a max? You have a vector, you take the max of a vector, you get a value. What is the derivative of that thing? Meaning, where did that maximum value came from? It's the argmax, right? So if you have a vector, you have three values, right? -7, 3, 5, 2, -2. You take the max, you're gonna get 5. You take the derivative with respect to the inner thing, right? You're gonna get 0, 0, 1, 0, right? Well, the derivative is equal to this, right? So this one changes the same way I change this one, right? If I turn this one to be 6, 7, 8, this one will change the same. So it's going to be a 1 corresponding to the arg maximum, right? 0 for all the other. If I change this to -7, -8, -9, -2, -1, it doesn't change anything, right? So the max derivative is going to be arg max, right? If I have a soft max, I call it this soft max, guess what is going to be the derivative? Soft argmax, very good. Anyway, this is like a probability, right? Anyway, so that's like a probability distribution. So these arrows, now, the length, the direction is the proportional to the distance, right? The magnitude is proportional to the probability the model assigns to that specific latent. In this case, the probability is 1, because it's just 1, right? So it's deterministically, that point is the minimizer. Here I warmed up the system. There is a non-zero probability assigned to all these things, right? And so the major one is going to be this one, but then also this one and this one will have, right? How much is this probability? That's going to be the exp of this guy divided by the sum of all these exps, right? Okay, very good. This is just for one sample. Then you have second sample, you have other arrows. Third sample, other arrows pointing to that one with this amplitude scaled by this probability thing coming from the soft argmax. But then, if I train it, these points will move following the gradient, right? And so you end up with this thing, which is basically the same as that. But the point is that here, each point was moved around, right? Here, the whole thing get moved up. All right, so I would say we are done, but this was unsupervised learning. In the next 30 seconds, I'll tell you about supervised learning. And this is the conclusion of the lecture today, right? So self-supervised learning, conditional case, well, the X and Y, right? So where we started, here we started before, right? With this thing spinning. What we learned so far was one choice of X. X was equal to 0, cut. So I was just learning this ellipse there. Now we're going to be introducing the fact that this stuff follows a horn. So I also showed you before the untrained model, which was that smaller thing. Now I show you the untrained model for the conditional case. So I have my latent going on a line. That is the line. Whatever I discretize for sake of me getting things done. I have a decoder. I have my Y tilde that goes in circumferences because of the decoder. I have my target. Oh, I have predictor. Predictor means that I come to this space from somewhere else. From what was the other space called? The X space. Very good. And so we feed this not bold purple, pink X. Okay? Which is the 0 to 1 information where we are in the horn. And here we go. So this is my untrained model manifold. I just put a neural net inside the predictor, and this is the thing it shows me. The model produces very uniformly sampled because I sample uniformly, right? It shows me ellipses which change the magnitude as I'm changing the x along this axis, right? All right. So energy function. I have the C, I put a box, that's going to be my E. My C is going to be the quadratic square distance, Euclidean distance. My E is going to be the C. We already know everything, right? This stuff is exactly as before, but what's happened here? We have a predictor, so we have F1 and F2, and then we still have G, right? So what is this stuff? So F and G's mapping are a scalar, right? Either both X and Z are scalars. Two-dimension item. My F is a neural net mapping my scalar X to a linear layer with 8 units and a ReLU. 8 units and a ReLU. 2 units, okay? So I have 1, 2, 3 linear transformations. I go from 1 to 8, 8 to 8, 8 to 2. ReLU, ReLU, linear. Why this one linear? Because these are going to be my W1, W2 parameters, right? But those are changing as X changes, right? So as I change my X, this network is supposed to give me the horn. G is still my ellipse generator, but no longer has a single amplitude. The amplitude is now a function of my condition, right? The conditional value. And this stuff changes, and I learn. So I'm going to be learning this neural network. First, finally, we have some neural networks. Yay! Hi. Train manifold. So I have these Z and X and Z, and this is my train manifold, right? You can see the difference between this one and this one, because here these were sampled from a uniform distribution, right? So these were my randomly generated points, right, from my data generating process. This is going to be my network output. How do I know it's my network output? Because I sample, well, I uniformly pick those values, right? I have control over how I can generate things, right? So that's my outcome. How did we end up here? So you have the original points. I used the zero temperature limit. I found we started in this direction here, right? I started with this one, and I have my first horn. On this point, I find, oh, what is the closest point on the horn? I find the closest point on the horn, and I pull it up. Then I go another point. I find what is the closest point on the horn. Oh, sorry, the other way around, right? So, yeah, I take a point. I find the closest point on the horn, and I try to go down to that horn, right? I take another point. I find the closest point to the horn. Poof, right? So what's happening here is that you have your initial X, right? Let's stop this spinning thing. There you go. So we have an initial value for X. Let's say 0.8. Given that I have 0.8, I have many possible Y's I can pick from this guy, right? So let's say you said 0.8. We pick on one slice. I can pick one Y, right? I pick one target. From that target, what do? I go in this manifold. I can change Z, and I can go all around the ellipse until I find the Z that is the closest to my target. Right? Next, what do? Toof. Again, I pick another X, 0.2. Here, I pick a Y. Then I go in my manifold. I change Z until I find the... Finish my sentence. Which one? I find the closest one, and then I push it down, right? And I keep doing that, right? And when I push it down, what do I get? Well, I get the point to be matching my value, right? And so you end up with the gradients necessary, right? Whenever you move the points, if I want to move this point, to move that point, I have to change the parameters, right? So I compute the partial derivatives of the E with respect to the parameters, and then I update the parameters given that I perform a minimization with respect to the latent first, right? So I input something, I perform a minimization over the latent in order to find the closest point to my target, then I minimize the loss with respect to, well, this guy, right? This one doesn't have parameters. I repeat once again. I have an input, my pink bold x, well, it's not bold, pink x. I provide my input. I make a prediction. The closest point is that one. So I change my latent until I get closest to my target. And then, well, actually, I'm here, right? Hold on. I get an x. I produce an output. This is my y. I do here. And then what do? This is, what is it?
It's changing the parameters of the predictor.
Gradient descent with respect to the parameters of the model. Once again, I get a y, so it's a y here, then I get an x. I get an x, and I produce a initial value. How can I go from here, my y tilde, to my y check? How do I move?
Z first. Z first.
I cannot hear you.
Z.
Yeah, how do I find z? I had to minimize the loss, right? So I had to go until I align with this thing. So this is the closest I can get. If z is too powerful, I can actually get here. That's why we need regularization, such that I cannot get up to here. Finally, I perform gradient descent in the parameter space until I hit down the target. And that's finished. So future challenges are the fact that here you may have the G, which is no longer a product, right? Before we had the product. Before I told you G was the cosine and sine. Now I can also have a neural network there, right? So G, I don't know what it is. It's going to be a, whatever function, which is getting the latent and my encoder, right, my predictor. And more, finally, I can also have now a latent, which is no longer a scalar, right? Now, okay, that was a scalar, right? This is a ball vector, right? And so now we need a regularizer, as someone said online. Otherwise, as you are doing a minimization in the latent, you actually reach the target. You don't longer need to go there. And this was the end of this energy-based introduction lecture. All my videos that I teach at NYU are on YouTube. On my YouTube, there are visual effects and everything else. I wanted to talk to you about the generative models, adversarial models, and things. I guess you can watch them online. And I believe next semester I will also change slightly something in order to make it consistent with what we saw today. Okay? Questions before I say goodbye? Yes?
So, is that to have a toy example so you know that it's an ellipse? What you have now with G is that also...
Previous one, right? So here I already gave up. In this version here, I gave up the ellipse.
It's a neural network also for like choosing...
Correct. So now G is a parametric function. I no longer have the the prior knowledge that this was an ellipse. This can be a spiral, can be anything. And so this one has to find out. But then I still know that my data lives on a unidimensional manifold.
Okay.
And so it's a very big assumption to know that. If you know that, sure, you can have a latent that is one-dimensional. The point is that you don't know, and you never know how to choose this latent, right? Because if it's too powerful, then the model will cheat. You always can get zero free energy, right? You minimize. If it's too powerful, you can get everything there. That's why.
So the predictor won't be trained, and we will be missing that kind of prior knowledge to fine-tune the network then. Okay.
And this is exactly the issue we were facing when I was training the driving scenario, the one I showed you before with the predictive model for the cars, my inputs to that model were the previous state and the control, meaning I was providing the steering control, turn left, turn right, acceleration or brake. These are two-dimensional vector, acceleration, positive, brake, negative, steering left, steering right. So it's a two-dimensional vector. And my latent was 16-dimensional. So guess what? My latent was learning and encoding the fact that everything was turning to the right because it's been trained to figure out that everything was turning to the right, regardless of the fact that I'm turning to the left. So if I turn to the left, everything should be turning to the right, right? So if you're driving and you turn left, everything turns to the right, actually, right? Right, so the model was just cheating and figuring out that everything was turning to the right through the latent variable, which was too powerful. So we had to find ways of constraining the power of the latent. Yeah?
Is there any way of using the value, like once you finish the training phase, so you have a sort of energy value over the training set, which is a scalar value?
Yeah.
Can you, you can do this procedure for different dimension of the latent space. Are the values you get of this energy, final energy, comparable in some way? Say, I reached lower energies with this dimension of the latent space.
If you're asking if you change the dimension of the latent?
I'm asking if the value of the energy is relatable if the dimension of the latent space changes.
Well, if the latent is too powerful, you can, if this is bounded below, right? Because I've been always using square distances. So if the latent is too powerful, you're gonna see your free energy 0 everywhere. That's like, oh, maybe your latent is too powerful. Then you try to reduce the power of the latent, it's gonna be, oh, something no longer 0. Then maybe that's, a good compromise, but I guess it's mostly like cross-validation. As everything in this field, it's an empirical field. It's like we are trying to make planes fly, but then we discover aerodynamics like 50 years later, right? But when we start flying planes, we didn't know how aerodynamics was working, right? So right now we know things by empirically, like we have understanding of how things work. We don't necessarily have this kind of, know-how for this additional guidance of how to find this specific information. It's just experiment, right? Unfortunately, yeah, it takes time. That's why we use a lot, not SGD, but GST. You know what is GSD? Gradient Student Descent. You're kidding? I'm not kidding. I have 500 students. I assign them to all 500 students the same project. Then the winning student finally found something. You need to do that in order to be able to find, consistently working methods, right? You had to really run not just multiple seeds, right? Just really different strategies and everything.
So it's more like an evolutionary approach.
Yeah, I think so. I think so. I believe so, right? And the best fit survivor, right? So
the worst students don't get to go on the course, and the best do.
I mean, then I pass everyone, but yeah, I'm also recorded. Damn, okay. All right, more questions? Yeah.
Okay. Okay. So, if I understand correctly, you have each step in your optimization are actually doing 2 optimization.
Correct.
Is that the case outside the toy model?
This is always like that.
Okay.
So you always perform a optimization. So there are 2 options, right? In this case, when I used the zero temperature limit free energy, I was performing a minimization with respect to the latent first, and then I perform a stochastic optimization with respect to the parameters. Either you do that, or you actually, the other version, which is the nicer one, which is performing the marginalization. Usually that marginalization is an integral which is intractable, and there is a lot of techniques which are used for approximating that integral. For example, in my case, where I show you before the generation of those different future trajectories from the initial condition of the traffic scene, we were just sampling. We were just using Monte Carlo's approximation. So all the issues you have in Bayesian learning with these integrals, we also face here in the case you want to perform this marginalization, right? And then you can use other tricks and to go around this thing. And okay, something that is very interesting, you can also compute something, you can perform something called amortized inference in order to train a model here to give you a Z, and you end up having an autoencoder. An autoencoder basically trains an encoder to give you the optimal minimizer for getting the best reconstruction, right? So if you have this one going to encoder and going here, then you have an autoencoder. And that would have been the second lesson I was hypothetically giving today, but didn't end up like that. Nevertheless, you can find this video on YouTube, right?
Thank you.
Moreover, if you'd like to follow up with anything I've been doing, and also these slides are going to be going online, and you can follow up on Twitter. You can find me on the handle AlfCNZ. And then, again, you're going to get like a lot of spam from, this kind of stuff with educational content on a maybe kind of bi-daily, every 2 day notice, right? That's it. Thank you for your attention. You kept alive and awake until the end. It was, it's not easy. It's Christmas in 2 days. So thanks again for giving attention and asking questions, and for the ones also joining online. Thanks for being with us today, and I hope to see you the next time. Bye. You're welcome.